Okay, we're gonna begin in a few minutes. Hi, welcome to the stream. So, yeah, um, this afternoon we have the tensor analysis, and this evening we have measures theory. So, hi, can you hear me? It's how's the sound? Yeah, I can see the chat. So, yeah, um, there is someone. There's no sound. Isn't there? Is there no sound? Let me check. Oh, okay. Let me see from my end if there's okay. If this sound is okay. Sorry. Hi. Okay. Okay. So it seems completely fine. Okay, that's fine. So we will begin with where we left last time. So right now, just as a summary of progress. So right now we're in the domain of Riemannian geometry from a tensor calculus point of view. So it's going to be mostly computational. So yesterday we introduced the notion of a metric tensor, right? So and the notion of a Riemannian space. Okay, we do not pretend this is mathematically rigorous by the modern standard, but that's the general idea. So we introduced the notion of a line element, ds squared, right? ds squared. Think about this as a small distance squared, like this. Okay, once again, not rigorous. That's fine. You don't learn how to count from the piano axioms, do you? Right. So at a certain point, abstraction will fall into place, but right now it's just intuition and um, the actual tools you can calculate things with. And from there, we can develop our intuition, and this way we can carve a path towards the big theory. It's okay to learn complicated subjects such as differential geometry multiple times. There's absolutely nothing wrong with that, and you probably do so. You do have to do that um, if you're serious about it. Anyway, so here we introduced the notion of a metric tensor, and the metric tensor defines this quadratic form ds squared. Here, actually, where? Yeah, here. This is a metric tensor. My goodness, where is that? Yeah, here. The most general form of a line element for Euclidean space is this one. But now we're no longer just considering Euclidean space, but rather quote-unquote Riemann space and a Riemannian space, which in modern terms is called a Riemannian manifold. Okay, we skip the abstract definition of a manifold in this series. But so you can think of manifold as high-dimensional surfaces. Of course, that's just an analogy. I think that's good enough. And it is equipped with this notion called Riemannian metric, and it's defining data is G alpha beta. This is a quadratic form, and in the language of tensor calculus, this is a second-order covariant tensor. So remember how we talked about how we defined covariant and contravariant tensors in the previous live. So this is a good afternoon. Thank you very much, Marco. Thank you for joining the stream again. So this is the metric tensor. We defined it last time, and this is the fundamental object of study in Riemannian geometry. So with this, you can do things like calculate distance and measuring angles, that sort of thing. It kind of plays the role of the inner product in linear algebra. So from the start, linear algebra starts from vector spaces with no extra structure. So from in a bare vector space with no additional structure, you cannot say the length of a vector. You cannot say the length of a vector. You cannot say things like angles between vectors. Right. So the classical intuition of a vector no longer works because in high school we tend to think of vectors as a quantity with magnitude and direction. But in a general vector space, there's no such thing as magnitude. Magnitude requires a notion of quote-unquote norm. Right? Not all norms come from inner product, but is still extra structure. In a Riemannian geometry, we have this notion of a metric tensor. So it just plays the role of the inner product. It allows you to measure length, measure angle, that kind of thing. And if the quadratic form can be diagonalized into a quadratic form defined by Kronecker delta, then we call the Riemannian space Euclidean. Right? Of course, from linear algebra, we know you cannot always do so. Right? You cannot always convert or diagonalize a quadratic form you can always diagonalize. Yeah, it is possible. You can always diagonalize thanks to what we call the principal axis theorem in linear algebra. Right? It's linear algebra. And by the way, if you want to take a quick review of this stuff, this is an excellent resource. Sorry, this was the Russian stream I did earlier. Anyway, so let's come back to linear algebra. So yeah, I always use this free resource offered by my home university. I mean, I'm no longer in the university. I graduated years ago, but this is what I use a lot of times still, because this, I mean, I took the course from there, so it's more convenient for me. I know the structure already. So yeah, that's basically the free resource on linear algebra I was talking about. So if you go to the home page, you can see linear algebra 1, linear algebra 2. For differential geometry, you need to be, or just tensor calculus in general, you need to be extremely familiar with the standard linear algebra stuff. Okay, matrix multiplication, vector spaces, quadratic form. Yes, we'll see geodesics, yes. Although I'm not quite sure if we'll do that today, because I want to do things like slow and steady wins the race, because if I just not randomly, but just go over the definitions as if they were given information, we're not going to have a great experience. So orthogonal diagonalization is useful for diagonalizing quadratic form. By doing that, we mean eliminating the cross terms. By introducing a transformation, a coordinate transformation, you eliminate terms such as x1, x2, x2, x3, and so on. You can always do that. You can always do that, but you cannot guarantee that the transformed version, you cannot guarantee to make sure all the coefficients are the same. If the coefficient lambda 1 all the way to lambda n are all the same, then you can scale it and write it as a quadratic form defined by Kronecker delta. This is not always possible. Right? For example, here you have a concrete example, 12 minus 8, 4, 4. So obviously you cannot scale them into a Kronecker delta because of the sign difference. So remember the Kronecker delta defined by quadratic, the quadratic form defined by Kronecker delta is a sum of squares. It's a sum of squares because the off-diagonal terms of Kronecker delta are all 0. Right? So it should look like ds squared equals dx squared plus dy squared plus dz squared. So it's non-negative. And obviously for this example, this quadratic form, it is not always non-negative. So what I'm trying to say is, even though you can always diagonalize the quadratic form, you cannot always bring it to this format. If that's possible, if this is possible, we call this a Euclidean space. What we see without functional, what do you mean functional? Functional analysis? You mean calculus of variation? Perhaps we will see some calculus variation, if that's what you're saying, because you're trying to minimize the distance, right? In the derivation of geodesics, we're highly likely, I don't know how the textbook is organized, but it is highly likely we will see some calculus of variation. Actually, calculus variation, that won't be very difficult, at least as far as the derivation of the critical condition is concerned, also known as the Euler-Lagrange equation. But we're still, like, the key here is still tensor. The key here is still tensor, working with tensors, knowing how, in particular today, our goal is to understand Christoffel symbols. Because Christoffel symbols is going to be very important, even in information geometry. So far, everything we did is completely foundational, okay? No specialization. yet. Okay. Anyway, so let's begin our today's lesson with or seminar. Okay, more. I tend to like to regard this as a seminar because, as I said, I'm not a lecturer. So anyway, with that disclaimer out of the way, let's take a look at the problem. So here we're going to define so-called reciprocal tensor. And it appears in the text as a problem. So if you're interested, you can check out section 126, problem 4. Problem 4, and this is on reciprocal tensor. Reciprocal tensor. So that's the setup. So that's the question. It says, so the question statement says, if A, alpha, beta, lower indices, so this is a covariant second order tensor. If A, alpha, beta are components, let me just turn off the sound on my phone. Components, it's my phone, not yours, okay? Are components of an absolute covariant tensor. Okay, what this means is it satisfies the transformation law as follows: A alpha beta equals A bar alpha beta equals Aij. I'll add the indices later, but this is okay. So if it is a covariant tensor, it transforms according to the inverse Jacobian. So dx over dx bar, and then dx over dx bar again, because there are two lower indices. All right, so and I'm going to add the indices in Jacobian. The first one should be di over dx bar alpha, and then the second is dxj over dxj beta. And yesterday we spent quite some time on how to write the transformation law based on the index position. Okay. Anyway, so that's the meaning of this sentence. So if A alpha beta are the component of an absolute covariant tensor, which means it satisfies this law, then and if say big A alpha beta upstairs, big A alpha beta upstairs times A beta gamma downstairs equals Kronecker delta alpha beta alpha gamma. Okay, and if this is also true, show that A alpha beta are the components of an absolute contravariant tensor. Show that A alpha beta upper indices are components of an absolute contravariant tensor. Okay, so what do we mean by that? So first, let's write down our goal. Proof. Need to show A alpha beta upper case satisfies the law of transformation for contravariant tensor. So A alpha beta bar, okay, A bar alpha beta, that's the new component, equals A bar ij. And then put the Jacobians on. So because this is a contravariant, so this is d new over d old, like this. And also two Jacobians all forward. Okay, so you need upper beta down upper stairs, and ij's are summed over, like this. So you need to show this. All right, so let's begin. Okay, so starting from this condition, A alpha beta, so we're given A alpha beta upstairs times A beta gamma downstairs equals Kronecker delta alpha gamma. Okay, there you go. And so we want to show that. We want to we should probably use the fact that the Kronecker delta itself is a tensor. So we showed that yesterday, right? We showed that yesterday that the Kronecker delta symbol itself is a tensor. So let me just write that statement down. So delta bar beta gamma beta alpha, this is delta aj dxj upstairs, okay, dx bar alpha downstairs, dxi upstairs, and then dx bar beta downstairs. So we have that. Right, so this way perhaps we can introduce a Jacobian into this equation. We want to show this transformation law. All right, so let's maybe start from there. Okay, so delta let me use a different color. So this is not definitive. Okay, so let me just do the exploration. So delta bar alpha beta alpha equals delta ij, the two Jacobians. Okay, use the expression for the delta. So put in a big A. The components of Aij also transform. No, we haven't done any transformation yet. Okay, so we need to show this. Okay, this is our goal. Okay, so this is our goal, and so this is our goal, and this is the green equation. You didn't write it that way. You mean this one? This one is from yesterday. Remember here, yesterday. The first example we did yesterday was to show this is a tensor. It's the same equation. Yeah, this is the same equation. The fact that delta is a tensor. Green is covariant. Green is covariant. Hang on a second. You see, this is right? You see, this is right. So the beta is contracted. The free indices are alpha, beta. So it should be delta with two indices, one up, one down. Not delta, the green for A. The green for A. The green for this one. This one is the definition for the covariant tensor. Yeah, so in our assumption, we assume that big A alpha beta downstairs is absolute covariant. Yeah, is absolute covariant. So this is a transform. Left hand side is transformed. This is a new one. And it transformed used according to the backward Jacobian. Like that. The green for A. Is there a problem with this equation? Okay, I'll explain my thought process again. Left hand side is the new component, A bar alpha beta. On the right, that's the old component, and it transforms according to the old Jacobian. Not old Jacobian, but backward Jacobian. So that's what we wanted. And now we need to show this. We need to show this. So I was thinking perhaps we can start from the given condition. and work our way from there. So actually, there's a mistake here. My bad. Here, there shouldn't be a bar here, you see? This is nonsense. It should be Aij without a bar on the right. Um, so is it, yeah, is this okay? Is this okay? Sorry, Marco, I got confused. So I think this is okay now. This is okay now. Okay. I yeah. Okay. My bad. Yeah. Sorry for um the lack of the lack. I mean, you tried to correct me. You're completely right. I made a mistake. Thank you very much. All right. So there we have this, and I was saying I tried to start from this, right? So I started from this, and the fact that Kronecker delta symbol itself is a tensor. Yeah. I was sloppy. I was sloppy. No, you're not crazy. Okay. So, how do you express delta? How do you express delta? Well, you get AI with a alpha cannot be used. So let's use gamma. Gamma, yeah, gamma is okay. AI gamma times big A gamma J times big A gamma J, and then paired with the Jacobians over here, paired with the Jacobian. So, and let's see what we can do here. So yeah, we substituted. Okay, I think I can get rid of this one. And it looks like we can use the transformation law for A alpha beta, right? For A uppercase alpha beta. Can we do that? Well, not quite, because on the right you need A I gamma, A I gamma, but wait, hold on, something is messed up here. This is not good, because why are we having two I upstairs? Did I mess up the? Did I mess it up? Oh yeah. So beta here should be up, I should be down like this. Beta should be up, I should be down. Beta should be up, I should be down. Yeah, that's better. That's better. And now how can we go? How can we use this condition? Well, it looks like we have A I gamma, which is good, and uh, dx beta over dx bar I. This way I is contracted, and we still need something else that contracts the gamma. So let's do that. So on the right we need A I gamma dx beta over dx bar I. Okay, and then we need to contract the what's that? The gamma. So you get dx here over dx bar gamma. Dx bar gamma. Okay, so here what would be a nice choice for the upper index? Let's just use mu. Okay. Yeah. So that should be fine. And this is according to the transformation law. This is a bar. This is a bar beta mu. This is a bar beta mu. All right. And then uh, we still have terms missing. So I have this term and I have this term and added an extra term. Okay, so I need a gamma j downstairs dxj over dx bar alpha. Okay, all right, great. So on the left, because we multiply by this extra factor, hold on a second. That's not a good idea. Hold on, that's not possible because gamma is not free. You can only contract free indices. Gamma, this does not work. This does not work. Okay, I'm in trouble. Looks like I'm in trouble. Okay, so this is invalid because I was saying, oh, here, but here, I want to create a law for a alpha beta upper stairs, but gamma is already contracted here. This doesn't work. This doesn't work, so let's just set this aside, okay? Maybe still, you know what? We're gonna leave this equation because this still might be useful, but this is not okay. You see, I'm very rusty. I don't. Okay, so can we say A alpha beta? Can we do that by saying, how do you see the gamma wasn't fixed? How do you see the gamma? Here, I tried to substitute. Yeah, so I wrote this as. Okay. Let me just. Yeah, so this was everything before I deleted, right? So on the right, here, I replaced this delta ij by the product of those two. So you see, gamma is repeated. So that's not a free index. Okay, so here you see this step right here, I'm trying to contract an index that is already contracted. So this way, you see, you see how absurd this is. I have one gamma upstairs and two gamma downstairs. So this expression now makes no sense. Okay. Perhaps. Okay. Perhaps. I mean, the thing is. Can I just erase this part? Okay. This is the part where things falls apart. So let's just erase this. So this is still okay. So can I maybe extract this thing? Maybe extract this thing. That will help us. Right? So, Kronecker delta is this. Yeah, so this can also be written as A bar alpha beta upstairs and A bar beta gamma downstairs. Yeah, I saw you, Shady. You were in JC stream. You're in JC. I mean, if you're interested, like, I mean, I'm a complete novice when it comes to that. But if you want something to be worked over like this, I mean, I don't promise completeness. I mean, if you like send me 10 books, I can't do. I mean, if you send me one book, I can't go over it. Okay, but if you just want to see how do you approach it, how do you get started, like you can post it on my Discord. I mean, and this way, perhaps there's more people to help you out there, and I'll try to find this time slot to stream this. Okay, so yeah, yeah. So Shady, if you're interested, like post whatever you're interested, the topic and even I mean the name of the material, or even better, the material itself. Okay, we'll try to help you there. Okay, so what I was saying is, how can we extract AI gamma upstairs? How can we extract AI gamma upstairs? Can we do that? I mean, let's try to move the Jacobians to the left. Let's do that. So, so we have this expression. So how do we get rid of the two Jacobians? So to get rid of the Jacobian delta ij, remember what's free. Remember what's free. Gamma and alpha are free. Alpha is free. So you need to get rid of the alpha here. So dxj, dx bar alpha times dx bar alpha. Yeah, no worries. No worries. I mean, there are a bunch of streams that were previously viewer requested. So this is what we do on the channel. dxk. The dxk. So I added this extra, I multiplied this extra term. So on the left, you got a bar alpha beta, a bar beta gamma, and then dx. I can't use alpha, can I? Sorry, this is completely messed up. My goodness. Oh, actually here, I'm trying to say is the left-hand side, this shouldn't be, I forgot the index again. I forgot the index again. Okay, so this is correct. Everything here is correct, but on the left, this is not correct. So beta is up, alpha should be down. Beta should be down. So it should be beta alpha. Right? Look at this definition. So beta is not contracted. The second index upstairs of the first term, a first factor, should be contracted. So let's say this is mu. Beta a beta mu upstairs, and then times a bar mu alpha. Okay, yeah, this is now okay. Okay, so let's do that. Multiply by that Jacobian. By the same Jacobian, we just multiply on the right. So it's dx bar alpha over dxk. Okay, so that's good. That's good. And then, of course, we do this to give ourselves a Kronecker delta jk. Delta jk. All right. And the second Jacobian is handled similarly. Dx beta over dx bar I. All right. So beta is free, so beta needs to be contracted. So you get x beta, yeah, dx beta, lower on the downstairs, and then dx. I need an extra letter. Say L. Okay, so this is dxL over dx beta, and this gives us the Kronecker delta Li. So that's the extra factor we multiply. So on the left, you have also dxL over dx bar beta. I know this is perhaps not the most elegant way. We're just exploring things. Okay, so those two Jacobians are now paired with their inverses. So this should reduces the term on the right. This should reduce the factors on the right. Okay, so this is what we have so far. Okay, so and now on the right, you just swap index according to the Kronecker delta. AI gamma times delta Li gives you AL delta, AL gamma, yeah, so I'm saying that again. Here, you swap I to L, like this. And second, you have A gamma J delta JK. So swap J to K. So this is A gamma K. A gamma K downstairs, okay? So that's it. And on the left, so is there anything we can do? Is there anything we can do on the left? Well, we want to show this, right? Want to show this. Did we use the law for big A bar yet? We haven't. We haven't. So big A bar is what? So what we want? What do we want here? Well, we want this. We want this. And big A bar alpha beta downstairs is this. Is it closer to what we're getting at? Still not quite. Still not quite. So, okay. So let me just put it here. So just stare at this and our goal, because so far we haven't used much, right? I mean we use what do we use? Okay, we use the transformation law for the Kronecker delta, and we use the given condition. This is given. This is a reciprocal condition, and we multiply the inverse Jacobian on both sides. This is what we got. Quick sanity check to see if the indices match. On the right, you have free indices LK. Here you have free indices, yeah, LK. So far so good. So far so good. What is this business here? So I mean, we wanted the uppercase transformation law. We wanted the uppercase transformation law. So perhaps it's not a good idea to. It's not good idea to get rid of these terms on the right, huh? We want the A bar alpha beta to remain here. Hmm. We want to show this is a contravariant tensor. So, hold on, let me see. How do we, I mean, perhaps this is not needed. I mean, this line is correct. I mean, this line is correct. So, but based on our goal, not based on our goal, considering our goal, I think we should get rid of this term. I think we should get rid of this term. So, how do we do that? Well, A bar, upper bar, beta alpha. Actually, you know what? Here, let's use the transformation law for A lower indices. So okay, I'm gonna just leave these here because this is still correct. It's just I don't see the usefulness. And now A bar, okay, use the transformation for A bar lower indices. Can we do that? Okay, so here, A bar beta mu, A bar beta mu times A bar alpha beta, A bar mu alpha. A bar mu alpha according to this law is okay, Aij, lowercase ij, and what? Aij, this should be easy exercise now. So dx over dx bar, dx over dx bar, mu alpha should be downstairs, ij should be upstairs. So yeah, you see, here I'm using the transformation law for a contravariant, for a covariant. This is what I used. Okay, so right hand side so far there's no manipulation. Okay, so far there's no manipulation, and see if there's anything we can do. Is this a tautology? I mean, is this a covariant? This is a covariant transformation of beta mu. Okay, I just did this. Okay, this is a covariant. Yes, this is x bar should be above. No, you mean the blue part, Marco? X bar should be downstairs because mu and alpha are downstairs. Okay, this line above was the same as this one, which we established is correct. Okay, I'll wait here. Okay, so a bar alpha, a bar mu alpha was comes from the fact that a alpha beta is absolute covariant tensor. Okay, and now what we have seems like we can shuffle some terms. Is that what we're is this? Seems like we can. Okay, so this is what we have so far. I can get rid of this now. Okay, and so what else is going on? Okay, actually, I think it's perhaps useful to revisit a main text on quotient law. So we did that a while ago. Okay, so let's just leave it now because I'm a little bit stuck here. So let's go to what we did on the 25th here, where we discussed the quotient law at the very end. Let's just copy this and place it right next to our exercise because I feel like this is very similar. So the quotient law says, suppose AI BJK. Suppose AI BJK is a tensor for all covariant, for all contravariant vector, big I, a big I, sorry, big AI. So that's the assumption. We want to prove BJK is also a tensor. I want to prove this is a tensor. So, okay, so first let's use the tensor law for the product, which reads this: AI BJK, A bar I, B bar JK, okay, is A alpha B beta gamma times a bunch of Jacobian. The Jacobians are determined by the index location. And here we just use the fact that the A is a contravariant vector. So A alpha and the 4 Jacobian combines into the new coordinates, the new components for big A. And since A is arbitrary, now you can have this cancellation. Actually, is that okay? Yeah, this is okay because A bar is arbitrary. You can actually say that. So, what we're dealing with is something similar, no? We have a product relation. And now we want to show that I think that this is very similar in spirit. So perhaps we should start from this. Yes. So this is, I think that my instinct is correct. So Because of the product a bar beta mu, a bar mu alpha, it's just the Kronecker delta, which makes it a tensor. Which is make it a tensor, so you can use the tensor law and get this. Right. So yeah, so this is the tensor law, and what the fuck is like a tensor, bro? Well, you have to watch the first 3 streams. Basically, if you, yeah, this is a tensor. It's a definition of tensor. It's a multi-indexed array that satisfies certain transformation law. Okay, that's the classical definition, and we motivated that through various examples and reconciled it with the modern definition. Okay, so yeah, so there's 3 levels of understanding when it comes to tensors. First, it is a multi-indexed array. Second is the definition we showed earlier, a bunch of indices, a quantity with a bunch of indices that satisfy transformation law. The third level is elements of tensor product spaces. It's like how you approach the notion of vector. In high school, you learn that vector is an arrow or a stick, right? Is a magnitude with direction. And later on, in elementary linear algebra, you learn, okay, it's a it's an n tuple, right? You have a bunch of components in it, vectors in Rn essentially, and then you learn that, oh, it's actually elements in the vector space. Different levels of abstraction. So anyway, let's come back to this derivation. I mean, what did I miss something? Did I miss something here? How can I here, you see, in this definition, we were able to use that AI is a contravariant vector. So here we wanted to use the fact that a lower beta alpha beta is covariant. So we wanted to do something about this. We desperately need to do something about this. That was the original motivation, and it failed. Because gamma is already contracted. Gamma is not free. My goodness, this is killing me. Maybe multiply the left side so that you get 2 delta function. Or maybe exactly 1 plus the correct Jacobian appears on the right, and Aij stay on both sides. Yeah, so this is a quotient law. But actually, quotient law says what? Sorry, here. I mean, what is our law here? This is the expression for the transformation. So you see, I'm desperately trying to do something about this. Something about this thing. Is it? Hold on a second. Is this right in my face? J is contracted. J is contracted. See? Not quite, huh? Not quite. Not quite. Okay, so let's not waste time any further, because I mean, not wasting time, but I guess it's fair that I put up a fight. Okay, so let's AI this. Okay. So here, let me AI this. Okay. So the question is, the question is, so if let's say given a LaTeX, a alpha beta is absolute contravariant, tensor, and absolute, and a lowercase alpha beta is absolute covariant tensor. Can we show that? Oh, no, not given this. We want to show this is a covariant tensor. Hang on a second. Hang on. We want actually we were given the lowercase. The lowercase is absolute covariant. So given covariant and upper a alpha beta, lower a beta gamma. Sorry about the LaTeX. It might look confusing, but this will get cleared up soon. Okay, so is delta alpha lower score beta. There we go. Typo. Okay, so presumably you mean a alpha beta is absolute covariant, and upstairs this is delta, and you have a upstairs beta, a beta gamma lower is delta alpha beta. Can we show that? Answer is, can we show that a alpha beta is absolute contravariant? Okay, so it uses prime notation. That's fine. This line comes from a alpha beta is absolute covariant. Yes. D old over D new. Okay, this is correct. By definition, we need to find the transformation. Okay, so yeah, this is what we did. We wrote that. We wrote that, and then substitute the transformation. Hang on. And then multiply delta. Okay. Hold on. What did we do wrong? Ah, we transformed the delta. We transformed the delta, which is unnecessary, no? We transformed the delta, which is, we should have substituted this at this very step. I mean, we did do that later. We did do that later, so perhaps it's just, yeah, we did that later here, like here. Okay, so let me rewrite this. Let me rewrite this. Okay, so compare with what we have earlier. I mean, I committed to the transformation of delta, and I think that's unnatural. You should just substitute the transformation for what's given right away. Yeah. So, guys, so let me just delete whatever that is unnecessary, because we don't need to show delta is a tensor, right? We know this is true. So we don't need to transform delta. That's unnatural. That's unnatural. So instead, we should just substitute the transformation for A alpha beta lower index down here. So I think that's where we get lost. Also, we're distracted by this unnecessary information here. Okay, so let me just remove that. Okay, we don't need that. Actually, this will be enough. This will be enough, actually. This will be enough. This part is enough. And everything else is unnecessary. Okay, so we don't need this. Okay, great. Okay, so coming back to this. Okay, so let me change the color. So this should be useful to blue. Okay, so yeah. So given we have this relation, we have the next equation. We have this. Okay, and then substitute the law for the A covariant. For A covariant. Can I freaking erase this? Thank you. Yeah, here. Okay. And then we have the delta on the right. Delta beta alpha. So what do we want? We want this. Remember, we want this. I guess it's a matter of getting rid of the Jacobians, right? So let's do the inverse Jacobian. A bar beta mu aij. Okay, first one, delta xi over not delta, dxi over dx bar mu gets paired with dx bar mu over I can't use j, let's use k. J is contracted here, so let's say dxk. Okay, and this gives us the delta I over k. Okay, and you multiply by the same on the right, so dx bar mu over dxk. Dx bar mu over dxk. Okay, great. And here you have dx, the second term, so second Jacobian, dxj over dx bar alpha. Multiply that by dx bar alpha over dxk. I can't use k, let's use L. Okay. dx bar alpha over dxl. Okay, so there's that. And delta beta alpha. Delta beta alpha, okay. So here this is the delta jk. Delta jk. Delta jk, okay. And so on the left, by the index swapping. By the index swapping, what do we have? First of all, are the indices still match? On the left, what are free? I is not free. K is no L here. This is L. Delta JL. I'm not reading chat for the moment right now. Okay, sorry. I'll read chat when I get stuck or when I finish. Okay, so here you have AIJ. I is not free. Yeah. J is not free. K is not free. Actually, K is free. L is free. Beta is free. Mu is free. So on the right, beta is free. Mu is free. K and L are free. Okay, so that's fine. So on the left, by index swapping, A bar beta mu times A big A. Okay, I gets swapped to K. J gets swapped to L. Hold on a second, this still doesn't make sense. Okay, on the right, first of all, let's do the index swapping. So just swap alpha to beta. Dx bar beta over dxl. Like this? Yeah, yeah, yeah. Thank you, Janice. So I think this is what we're getting at. However, what do we want? Well, we need it upstairs. We need it upstairs. Okay. So now can we use the old delta again? Can we use the old delta to create a to get rid of this thing? You know what I'm saying? So remember what we wanted, right? We wanted this. And now it's okay, compare our goal to what we have. On the right we have two Jacobians. And the order is correct. Bar coordinate is on top. So let's multiply that by multiply this A upper two indices thing. Okay? So this is what we want. So this is our goal. Our goal. So on the right, things are already looking quite promising. So let's keep rolling. On the right, okay, so this is two Jacobians, which is nice. And now we need to contract the two lower indices based on what we've seen here. We need to contract the two lower indices. This is our goal. So let's contract that. So here on the right, mu, beta, KL are all free. So let's contract K and L. So multiply that by big A, KL. Simultaneously. Okay, on the left, you do the same thing. This is what's on the left. And then you multiply that by, hold on. And then you multiply that by AKL. Is that a good idea? This will give a two contraction, no? This is what we wanted. Remember, this is what we wanted. Yeah, because I mean, I was still trying to use this. Okay, I think we're getting close, but still, this index is still a little bit of a mess. Okay, so let's ignore this term now. So okay, so far this and this has no difference here. What do I want? So this is AKL. AKL. Okay, AKL. AKL times A. If we contract the first index K, let's say AIK. Okay, let's say AIK upstairs times AKL downstairs should be delta IL. So let's do an AIK. Let's multiply by AIK on both sides. This is AIK on the right, and this is AIK on the left. And this gives us a delta IL. And since we have that, the left hand side index gets swapped. No, there's no swapping. It's all still free. There's no index swapping here. Everything is still free. You got four free indices on the left and four free indices on the right. That's fine. I mean, this is still valid. Perhaps now set the K and L to be the same, huh? No, not set K and L to be the same, but rather set L and I to be the same. This would indicate a contraction. Is that how it works? Is that how it works? Let me, okay, ChatGPT, help me out again. So, proof, okay, so start from the given condition. Yes, this one. Substitution, this is what we did. Multiply inverse Jacobian. Yeah, so we have this. So far we have this. It says what? Finally multiplying. Yeah, finally multiplying. It's a matter of renaming indices? How come? So A rho lambda times A lambda sigma gives you this. Okay, so yeah, I'm just wanted to see. Okay, I'm using ChatGPT's notation. So this part, how does that work, huh? Sorry. How does that work? Okay, let's do that. So you have using ChatGPT's notation, A alpha prime beta prime, A rho lambda times A lambda sigma, right? That's the delta sigma rho. And this is, well, because we multiply A lambda sigma. This is, I think this is exactly what we did. Dx alpha prime, dx lambda, dx beta prime over dx rho. Right? I think this is exactly what we did. But how do you just get that, huh? Just like this? And it's not, we're not even renaming indices. So you say on the right you get A lambda sigma, yeah? And the two Jacobians. But on the left, how did you just get... This is supposed to be A alpha prime sigma prime. What the... So I think I'm still having trouble with the last step. Explain the last step in the index proof. Yeah, multiplication, this is delta on the left. Yes, this is what's on the left. How do you remove the Kronecker delta? Wait, why is rho summed over? Rho does not look like it's been summed over. On the left, you have four free indices. That's what I was saying. So it's multiplying by this factor, I guess. I guess you can multiply by this again. Huh? Is that what it's doing? Thus 2 is this. We have this, remember, we have this. We have the delta on the left. Exactly like here, but I don't know, like, what the? Guys, do you see? Yeah, because it will give us to the previous definition of delta, no? Um, guys, I'm sorry. I'm really sorry because um, I'm I'm completely and totally blind right now. So you see here, we were able to get this. How do you remove the Kronecker delta? There's no index swapping can be done here. So to get the transformation law, right? So you get to the final answer, your mu and sigma, mu and nu needs to be summed over, but here lambda is summed over, rho and sigma are not contracted. So you guys, I guess you need to just contract. So two. Oh, so okay. I'm gonna ask a question. Are we contracting rho and sigma in equation 2 above? Why is this a problem? Come on, AI. Are you serious? Just stand your ground if you're. What the fuck? The clean proof is by verification and uniqueness. What uniqueness? You mean uniqueness of inverse? I see. I see. So what? So you see, AI completely disregarded what everything we just did, and instead the cleanest proof is by verification and uniqueness. So it's like we're assuming this, huh? We're checking the right hand side works essentially. So we're checking the right hand side. So we're checking the right hand satisfy this equation. We're not computing this. We're checking the right hand side satisfy this equation. So now it's a completely different strategy now. Okay, that's bizarre, but at the very beginning, when I first asked the question, there is a matrix proof. Perhaps we can decode something from there. It says there's a shorter argument. Treat A alpha beta as a matrix A under a coordinate change. What is that? What is that? This looks like similarity. Okay. Anyway, this I don't get it. Okay, I still don't get this one. But if we just ignore everything we discussed, so I was stuck here. Remember, I was stuck here, so I wasn't able to remove the delta. If we wanted to remove the delta, we do a quote unquote contraction. Actually, if we get this, can we just say, okay, when I and j are equal, say when I and j are equal, okay, so let's say if we already have this and we say, oh, when I and j are equal, the left is just a bar beta mu, and on the right you just get an I and you can't do that, huh? You can't do that because on the right, if you set I and L to be equal, you have a summation. Like right now, there's no summation here. To get this, you need a summation. And if you sum over this, you get n. I would like to replace the I index in your delta function so it contracts. Remember, yeah, this is what we have so far. This is what we have so far, right? If you want to do an index contraction, say set I equals L, the left will become n. This delta symbol, when you set contract that, you sum over the diagonals, you get n. And on the right, there's no n. So something is wrong here. Jenny says, I would like to replace the I index in your delta function so it contracts with the contravariant tensor. You want to set, okay, so Janice is saying by setting a mu to be L, like that, setting mu to be L, but I want to remind you that still this is what we wanted, right? This is what we want. We want two free indices on top. If you're contracting mu, what happens next? So anyway, let's try that idea, huh? If that's what you want to go. Okay, so let's put this aside. Okay, so on the left, let's say you got a bar beta I, not I, but beta L delta IL. Actually, I don't even know what this sum up to because there's no index swapping. But let's just play along. If I replace mu to L, then the Jacobian gets summed over. You see, the Jacobian gets summed over, and that's not even. It just gives you just useless information. So, not helpful. Not helpful. I mean, as far as I can tell, okay? Maybe I'm missing something terribly obvious. But guys, if you have ideas, okay? I know the YouTube UI is limited, but if you have ideas, you can say if you're watching it from a what's that? If you're watching it from your PC, I suppose you can go to MS Paint or something equivalent in your MacBook. You just write something and send a screenshot to my Discord. Say it's like Ming, you idiot, you messed up this part. Okay, you just write that down and take a screenshot, send it to my Discord. And because it's difficult to type, right? It's difficult to type. My apologies. Okay, so we'll have to figure out a better format. Leo has an excellent platform where people can collaborate. So you can write directly there I might need to talk to Leo about this, see if I can borrow his platform or something like that, because that's a really nice way for people to collaborate. So yeah, I'll talk to Leo about this. So, but right now, I mean, you can just write something in Paint and send a screenshot to my Discord. Okay. As far as this session is concerned. So, okay. I'll take a look at this process and see how. I think this should, if I can. No, you're not too late. We're still doing the very same problem, started from the beginning, Andre. So today was a massive blunder. I mean, it's a good thing. It's a good thing because it exposes the fragility of my foundation. It's always good to have a humbling experience. Anyway, so this is what we're trying to show. Andrea, you're not late. Okay, we're still working on the same problem. So the problem is if you have a absolute covariant tensor, A alpha beta, which means it transforms according to this rule. And we have the second assumption that A alpha beta upstairs times A beta gamma downstairs is delta alpha gamma. We want to show that A alpha beta upstairs are components of contravariant tensors. So basically we need to show this. We need to show this law. Okay, so we need to show this law, and so far we've tried. You know, guys, I have this feeling that perhaps my model, like this is the free version of ChatGPT. I feel like it's not thinking; it's just sticking random text together, and if I call it out, then he makes up something later. So I don't know. Like this is kind of weird, but we are. I mean, not we. Perhaps you guys already figured out, but here I am stuck at this step compared to what I wanted. So on the right, you should have both indices in Aij summed over, contracted, whatever you want to call it. But I'm stuck with this fact that I cannot sum over the second index. Okay, so something is wrong, and perhaps something super obvious, I'm just not getting it. Which is okay. But let's just think about the strategy, whether or not the other idea given by AI is actually valid. So what we have, we have our assumption 1 and assumption 2. We want to show 3. Okay? We want to show from 1 need 1 and 2 implies 3. That's what we want. So, and because 2 here, 2 also implies 2 prime. This is 2 bar. Let's call it 2 bar. This is a barred version of 2. Okay, this is a barred version of 2, and if we assume that you have, and if we assume the inverse is unique, and by the way, I don't know, like, can we even assume that? Because the question did not say that. Perhaps we just proved a special case. Is that what it's about? I am totally in the dark here. Okay, so but let's just assume the invertibility, all that stuff. Okay, assume invertibility. Assume the what's that? Assume that A bar upstairs beta mu. This is invertible. Assume this is invertible. Okay. Actually, sorry. Actually, assume this is invertible. Actually, A bar lowercase, A bar mu alpha lower downstairs, whatever you want to call it. This is invertible. Then the left should be unique. So if we can just verify the right hand side of 3, satisfy the equation, satisfy 2 bar, then you're done. Okay, so this assumes invertibility, which is unsatisfying, which I don't think it should depend on invertibility. I don't think it should depend on invertibility. Or if you can show that's invertible, that's also cool. Okay, that's also cool. If you can show, actually, I don't think you can. I don't think you can. This is not. Actually, you can't. Given 2, 2 implies that this is invertible. Yeah, this is invertible. This is invertible. So if this is invertible, and Jacobians are all invertible, then this is invertible. Actually, yeah, that actually works. It just needs a little bit of a justification. It just needs a little bit of justification. However, I still feel dissatisfied because if it requires on invertibility, then this technique only works for a 2-index array. Because of 2-index arrays, the matrix, you have all these theories about invertibility and whatnot. But I think this should be something a generalization of this statement for higher order tensor should exist. But anyway, I'm just gonna leave here. Okay, so I'm just gonna leave things here for the 3 question mark. Okay, and I'm going to use the verification route. Okay, so let me explain that one more time. So here, another approach. Okay, so given 1, the transformation law for A alpha beta downstairs. So given A bar alpha beta is Aij times the Jacobian, because this is a covariant, so it's d old over d new, d old over d new. Yeah, that's right. Alpha beta should be downstairs, Ij should be upstairs. So given 1 and 2, 1 and 2, A upstairs alpha beta times A downstairs beta gamma is Kronecker delta, alpha upstairs, gamma downstairs. So we have that. Need to show 3. That's the conclusion that A alpha beta upstairs, A alpha beta upstairs is contravariant, namely A bar alpha beta is A bar Ij, okay, dx bar over dx, dx bar over dx. Now put the indices. What the indices we have? Well, alpha beta should be upstairs, Ij should be downstairs. Okay, so show 3. This is another approach. Okay, so this is another approach, and now we need to argue a few things. So given 2, proof given 2, this is saying that A beta gamma given 2, we have A beta gamma is invertible with inverse A alpha beta. Right? So just a matrix relation. Right? So, and by 1, you have A bar alpha beta is also invertible. This is invertible as well. Why? Because we just say A with 2 lower indexes is invertible, and the Jacobians is always assumed to be invertible, at least locally, right? So, and this way you get A bar alpha beta is invertible. So this is invertible. This way we have this is invertible. Okay, cool. Okay, so just leave it here. So by also by two, also by two, the we can add bar on both sides because by two and the fact that delta alpha gamma equals delta bar alpha gamma. Oh no, we don't need that. We and by two. Okay, let me just say by two. Let me just say you have a bar alpha beta upstairs and a bar beta gamma downstairs is delta bar alpha gamma downstairs, alpha upstairs, gamma downstairs. So we have that. So we have that. Okay. So this means, i.e., i.e. bar a bar alpha beta is the inverse. Is the inverse of a bar beta gamma. So we have this, okay? It's not something we need to show. This is what we know from the assumptions. So to show three, you just, by the uniqueness of inverse, the theorem in linear algebra, you just verify. By the uniqueness of inverse, to show three, suffices to verify that this expression for this expression, so the right hand side of 3 satisfies the inverse relation. So the right hand side of 3, this one, which is a alpha beta, and this is supposed to be a alpha beta here, times a bar beta gamma times a bar beta gamma equals delta. Question mark. So we just need to verify that. Okay, so details. The details. So the left hand side equals this thing times the expression for a bar beta gamma. Well, we know how to write that. That's just a. I can't use ij anymore. Let's use kl. The akl downstairs, and use the inverse Jacobian d, because this is covariant. So dx over dx bar, dx over dx bar, k upstairs, l upstairs, beta downstairs, gamma downstairs. Okay, so this is the left hand side. So let's left hand side. Let's group terms. So we got aij, akl. Can we group Jacobians? Is there anything to contract? Is there anything to contract here? Oh, there is, right? There is. So you see these two can contract. So, okay, let me write the term that aren't contracted. Okay, so this term stays put. The last factor stays put. Okay, what happens is this Jacobian and this Jacobian together. Hold on. Where's? Yeah, you're right. I'm right. I was correct. So beta is now contracted because beta is now contracted. You get dxk over dxj, which is a Kronecker delta. That gives you a delta kj. This gives you delta kj, and now you can, this gives you delta kj, and now you can swap indices. Swap j to k here. So swapping j to k, the first term now becomes a I k. Okay, and then times akl times blah blah blah. Okay. See what else we can do here. Well, this is in the definition. That's a Kronecker delta. So this gives you, by the inverse relation, this gives you delta ik, delta il. This gives you delta il, and now you can swap index again. Okay, just swap I to L. Swapping I to L, you get dx bar alpha over dxl times dxl over dx bar sigma. Not sigma, but gamma. Okay, so once again, that's just delta alpha gamma. Delta alpha gamma, which is exactly delta bar alpha gamma. These two are the same. Actually, guys, is this the same now? I kind of feel weirded out by this because delta is supposed to be a tensor. I always feel weirded out about this, but I mean, in fact, I have tons of confusion about the sessions we did earlier. I'm struggling to articulate, but where the hell is that example? To show the Kronecker delta is a I mean, here, as you can see, yesterday we showed Kronecker delta is a tensor. You see? So here, this question mark, the equation I put a question mark here is exactly this one. I actually had doubt about this. I mean, I guess you can say this is equal 1 if alpha and beta are the same, and 0 if alpha and beta are not the same. And the same is true for the second Kronecker delta symbol with bar. And you also have this transformation law. Oh, that's not a contradiction. This is fine. This is fine. So, okay, so there's no confusion here. There's no question mark here. There's no question mark here. Oh, so at least this route works out, right? So at least this verification proof works out. You see, our earlier approach was to try to calculate a bar alpha beta, to simplify this, to manipulate and simplify. But we don't even know what went wrong, did we? Like, I don't even know what went wrong. Right? So I don't know, like, after at this step, okay, so after this step, how can we go forward? How can we go forward to what we want? So that's the $1 million question. How do we get here? AI didn't seem to be helpful, but at least the verification method works. Okay, so now this is cleared up. Okay, so sounds good. Okay, so what is the point of all of this? Well, we spent like an hour and a half trying to figure out this proposition. I hope it's like, if you guys find this annoying, I'm so sorry. But this is like the process. I mean, my process. I mean, so I'm not saying the process. This is my process. I wasn't able to clear this hurdle even now, but at least this method works. So what are we getting at, right? Yesterday we talked about the the metric tensor. So continue. This is example 20, I believe. Yesterday we did, the last example is, last example is 19, I believe. Hang on. Yeah, this example should be 19. There's a labeling. This example, yeah, 18, 19, and this should be 20. So example 20. Example 20 introduces the reciprocal metric tensor. Okay. So we did earlier this work to introduce the notion of inverse, or sorry, say reciprocal tensor. We want the reciprocal tensor for the metric tensor. That's what we wanted. So yeah, I'll put a note in the comments of this stream. Once the recording is ready, I will just say, okay, at what point do we get to a workable proof, and even though the previous attempt is still unresolved, okay, to avoid wasting time if people want to watch the recording. So example 20 says the following. Example 20 says you can define the reciprocal metric tensor, which is as this. So gi alpha upstairs times g alpha j downstairs equals delta I upstairs, j downstairs. Okay, so this is the original metric tensor, this is the reciprocal. So yeah, this is the reciprocal metric tensor, and now we have two matrices, okay? Essentially you have two matrices. All right, so Gij, for example, in spherical coordinate, okay, Gij as a matrix, we calculated yesterday. I'm just going to put the results here, okay? So the diagonals are here. In spherical, the diagonals are 1 r squared and r squared sine squared, and the off diagonals are all 0. So you get 1 r squared sine squared theta. So that's the original metric tensor, and upstairs should be the inverse. And because this is a diagonal matrix, the inverse is easy. So it's just the reciprocal of the diagonal elements. 1 over r squared and 1 over r squared sine squared theta. Reciprocal metric tensor. All right. So there's that. Okay. However, of course, in general, Gij don't have to be a diagonal. Okay. So Gij in general don't have a nice expression. You know, the formula for the inverse matrix is almost always complicated. Okay, so now let's define the length of vector in Riemannian space, which really should be the length of vector in the tangent space, because the Riemannian space itself is, well, curvy, can be curvy. Once again, this is not a precise terminology. Okay, so imagine you have, this is a Riemannian space. Imagine this is like a torus. Okay, and at a point you have a tangent space. So you can imagine that's the tangent plane of a torus, and in there you have vectors. And the vector length is defined as follows. So vector AI in a Riemannian space, which really should be the tangent space, Riemannian space itself may not be a vector space. Okay, so this is not rigorous. This statement is not rigorous. This phrasing is not rigorous. So vector AI in the Riemannian space has length defined as follows: L squared, length squared actually. Length squared is G alpha beta, A alpha, A beta. Once again, a quadratic form. This shouldn't be any surprise because considering how the line element is defined. All right, so the associated vector of AI is a covariant vector called associated vector. The associated vector AI, A lower I. What is A lower I? So you guys, if you guys have exposed to a tensor calculus before, you might know things like index juggling. So going from upper index to lower index, lowering and uppering the index. To do that, you use the metric tensor. Okay, so let's say you have an upper index vector on the right. So let's say you have A alpha here, and you need to lower the index. So what do? You use a metric tensor. So this is the definition, okay? The definition of the associated vector, G I alpha. Doesn't matter if it's G I alpha or G alpha I because G is symmetric. You can write G alpha I too. Does not matter. All right. So this is the associated vector, and now you can easily derive. So how do you get, say, how do you get from from this? You can prove. You can prove that the reverse operation, say AI upstairs. AI upstairs is, how does that? How do you get that from the lower index vector? So let's say A alpha downstairs. You need to multiply by the metric tensor G alpha I on top. So G alpha I on top, this is what we have. And we can prove this. And here's a quick proof. Here's a quick proof. So use Kronecker delta. Use the fact that you have a Kronecker delta. So use the inverse relation, like the invertibility of G. All right. So here on the left, you have G I alpha, A alpha equals A lower, AI lower. A lower. So let's pair this with the G on the left with a with a metric tensor. So G on the left, and I is free, so we want to unfree that. So let's do a Gij on the left. So Gij on the left, multiply Gij on the left. This is what we have. Okay, and this will give us delta J alpha, A alpha, and Gij Aj, Gij Ai, which is exactly Aj equals Gij Ai. Right, so exactly as this one. What we want is a QED. Here's a quick proof. All right, so let me just highlight those definitions. The reciprocal metric tensor, that's the important definition. Vector in Riemannian space has length, given by this formula. Index juggling identities. And this works for tensors that are a higher rank 2, okay? Higher order 2. It doesn't have to be vectors. Okay, so and we can show that the length is the same if you use the if you swap all the index from lower to upper and upper to lower. So I'm saying. So here L squared can show that L squared by definition is G alpha beta definition G alpha beta times A alpha A beta. Okay, and the upper index transformation law is given by this. So you got G alpha beta. So A alpha, A big alpha is what? A big alpha can be written as G, say, A alpha, say this is G alpha mu times A mu lower. Okay. This is the part where we did the manipulation. And then times A beta. Well, A beta use the same business. You get G. Beta should be on top. Let's do a nu here. And then nu downstairs. Downstairs. Okay, so that's the second substitution. So let's see what can we do. Well, the first two g's gets multiplied to a Kronecker delta. So this is delta mu upstairs, beta downstairs, A mu, G, beta nu, A nu. Okay. Swap the index and you get G mu nu. Okay, G mu nu, A mu, A nu. Okay, so the point is that if you change all the alpha and betas from upper to lower and lower to upper, the length remains the same. Okay, so that's the conclusion here. Let me just write that as a separate formula. L squared equals G mu nu upper equals times A mu downstairs and A nu downstairs. So that's a useful fact. Okay, continue. So now we can define angles between two vectors. In Riemannian geometry, you can talk about lengths, you can talk about angles. So we just define length. And now angles. So example 22, which really should be definitions. Okay. Example 22 says the following: angles between two vectors. Once again, this should be angle between two vectors in the really should be two tangent vectors. Okay. Same setup, all right? So you have a Riemannian space, say M. This is Tm, the tangent space, and you have tangent vectors living in a tangent space. Okay. And now let's says let AI and Bj. So say A has the upper index and B has a lower index. So let AI and Bj be unit vectors. That be unit vectors. And we can define the angle between them. Define the angle as following. So as cosine theta equals AI BI. This is the definition. Okay, define the angle. The cosine, at least, cosine of the angle between them as such. Okay, and now we wish to calculate equivalent equivalent formulas. Okay, so how do you derive equivalent formula? So, well, now let's just use the G. Just use the G earlier. So we have equivalent formulas. Hi, Marco. Equivalent formulas. So when did you leave? Did you leave after we finished the proof of reciprocal tensor? Okay, let me know, okay? We'll quickly go over that so you can catch up. No worries, not at all. Don't be sorry. Could you solve the problem? Well, we did use the inverse approach. So the key here, so this is an entirely different approach, okay? We use the uniqueness of inverse. We use the uniqueness of inverse, and basically we just verified that what we wanted to show, the right-hand side of what we wanted to show, satisfies the inverse condition. Okay, so you can rewind this part of the stream later, but this is a completely different approach. So the idea is I was trying to derive an expression of A bar alpha beta, and the new approach is just to verify this works, and by uniqueness. So this has to be A bar alpha beta. All right, so that's the new approach. And now you have showed that the reciprocal tensor is actually a tensor. We can define the reciprocal metric tensor. And now we're in the process of defining lengths. We already defined lengths using the metric tensor. So the length of a vector, or more precisely, a length of a tangent vector in a Riemannian space. And now we're defining the angle between two vectors. Angle between two vectors in the Riemannian space. So in the definition, you have two vectors, AI upstairs, and my goodness, BJ downstairs. BJ down there. So one is A is contravariant and B is covariant. Okay, so the angle, and more precisely, the cosine of the angle is defined as AI BI. So I is summed over. And now we're just gonna give the equivalent formulas of this cosine expression. How do we do that? Well, use index juggling. So cosine theta, this expression can be written as follows. So why don't we change all the indices for the vectors to be upstairs? We can do that. So we can write Bj as B with an upper Bi, okay, with an upper index. So upper index B, so Bj. Yeah, this is Bj, and Bj, and then times what? Times the G. Should have an I downstairs, so it's a Gij. Okay? Index juggling. So that's one equivalent way to write this. Of course, we typically put the quadratic, not the quadratic, but double index letter or whatever this thing is. Okay, it's called a tensor. Gij at the first factor. So this is how we write. Not quadratic form, but bilinear form. Bilinear form. Gij AI. It's nothing but the dot product, really. It's nothing but the dot product. AIBJ. AIBJ. Remember how we looked over the notion of bilinear form on the 25th? No, this is statistic. Okay, so here. Actually 27. No, 27 was yesterday. Yeah, 25th. 25th. So we look at the notion of bilinear form, the modern formulation. You take two vectors in V and return the number, and it's bilinear. The most quintessential example for that is the inner product. So under a change of basis, the inner product stays the same. Inner product stays the same, so the component should transform according to this way. All right, and yeah, so you would have the yeah. So basically, um, a bilinear form in general has this general form. Okay, and cosine is really just a dot product. It's the same cosine formula in vector geometry in R3 or R2. So now you just write this as a generalize this. Actually, you just generalize this to the Riemannian space, Gij. So this might not be a Euclidean metric tensor. Okay, so just a Gij, Ai, Bj, and then you can say lower the index in A. So I want A with a lower index, so I would say Aj, Bi. So if you want to write Ai upstairs as A with a lower index, you need to use the other metric tensor, Gij upstairs. So that's another way to write it. That's another way to write it. Okay, so or you can write it as Gij Ai Bj. It does not matter. So here I'm just exchanging the index I and j. These are dummy index. I and j are both dummies. So exchanging them, you would have literally you have Gji, Ai Bj, but because G is symmetric, it's the same as Gij. Equivalent formulas. So there's that. Okay, so if the unit vectors, if they aren't unit vectors, so if the vectors aren't unit vectors, if they aren't unit vectors, then well, so just to have an idea of what this cosine formula comes from, that's in case that's not super obvious. So if you have two vectors in Euclidean space, cosine theta is defined as a dot b over a length times b length, right? So if a and b are unit vectors, it's simply the dot product. And here we're generalizing this to the what's that? The Riemannian space. However, there's something that needs to be resolved. Like, how do we know, say, this is a well-defined cosine? Like, how do we know this is less than or equal to 1? In Euclidean space, or in the inner product space, we know this is true. We can prove it using the Cauchy-Schwarz inequality. So now we need to show this actually makes sense. So basically, we need to prove the Cauchy-Schwarz inequality in the tangent space of Riemann space. Okay, so that's the idea. We want to show why this is well defined. Okay. So let me just finish writing this. So if the vectors on unit vectors, cosine theta is defined as Gij lower, Ai upper, Bj upper, and divided by Gij Ai upper, Bj upper, square root times the square root of Gij A no Aj, because downstairs is just the length of A and the length of B, exactly like in the Euclidean space. Quite straightforward. But we need to prove we need to prove this is well defined. This cosine theta absolute value is less than or equal to 1. Otherwise, this is a meaningless cosine. So we must show this. Okay, so proof. There you go. So okay. Hang on. To do this, we need to assume G is, hang on, G is, we need to assume G is positive definite. We need to assume G is positive definite, otherwise it's undefined. Otherwise, this might not be well defined. Okay, so let me just put it right at the beginning, because I hate adding assumption in the middle of something. Okay, so hold on a second. Yeah, let me just, because in text it actually introduced the assumption in the middle, which I'm not a huge fan of. So I'm gonna add the assumption at the beginning. So assume G is positive definite. Assume G is positive definite, that is G alpha beta times Z alpha Z beta is positive unless Zi's are strictly equal to 0. Okay. Assume this is positive definite, and now we can show the inequality, because if G is just arbitrary, there's no inequality to work with, so I guess you can imagine there's you cannot deduce this inequality. So now we can have something to work with now, assuming G is positive definite. Okay, so this really is a trickery also used in linear algebra, basically for proving the Cauchy-Schwarz inequality. That is to say, let's consider the length. Consider the length of the vector lambda a alpha plus mu b alpha. This is a linear combination of a and b. It's a linear combination of a and b, and it has to be non-negative. Right, so therefore, L squared of this length, L squared, that's the square length of this thing, it should be G alpha beta and then lambda a alpha plus mu b alpha and times the same thing. Actually, no, it should be, yeah, it's the same thing. Lambda a beta plus mu b beta. This should be positive. So just expand that. Or let's consider this as well, so okay, so yeah, let's write the left hand side as this, by the expansion you should have lambda squared G alpha beta a alpha a beta, okay, and then plus 2 lambda mu G alpha beta a alpha b beta and plus mu squared g alpha beta b alpha b beta. So that's should be positive, right? This should be positive, and you can treat this as a function. I wonder you're also learning with this when you're making stream. Yes, I'm learning. I'm learning. So it depends, right? Depends. So for certain areas, I'm more experienced. I think it's fair to say that. For example, the mathematical statistics stream, as I mentioned, is mostly me lecturing because I'm more experienced in that. My older stream tend to be me at least have a passing familiarity with the subject. Okay. So Andre, to answer your question, there are several streams right now going on the channel. Right. So the measure theory is like me revisiting the stuff. Okay. And mathematical statistics is perhaps the closest to lecturing. And this is for me. I mean, tensor. Although I did tensors like 10 years ago, but because there was so little opportunity for me to use it, or I just didn't have time to use it. So I'm not learning this for the first time. So I'm very rusty. Okay. So that's the idea. I just wanted to show, sometimes I show the process of how to approach a subject for the first time. Like, for example, the information theory stream. Right? For the information theory stream, I'm actually learning it for the first time. So that's like a one take, if you like. I guess it's that's why I always call my live stream similar to seminars rather than lectures, because I would very much nervous. I would be very nervous if somebody treat me like a source of information on this stuff, because I'm still in the process of absorbing it. Perhaps the point of doing this, okay, is, I mean, my original motivation of doing this is to show, okay, where are some of the most common things to get confused about, okay, and perhaps you can avoid my mistakes. Sorry for asking, Super. Why in general you need a tensor? Good question. I think I answered that yesterday. Marco, and for anyone else in the stream, if you guys already seen that part of the question, I apologize, but I do need to address this again because it has to do with no, don't be sorry. It's not a shame at all. It's not a shame. Okay, so I'll answer Andre's question on why do we need a tensor. Okay, but I did answer that question in the beginning part of yesterday's stream. Okay, but if you have seen that, I apologize, but I think this is important, so I'll answer it again. So what is tensor? Why do we need tensor? To study invariance. So, for example, invariance is the property of a geometric object that is independent of coordinate system. Okay, so that's invariance. And actually the final goal, at least the immediate big goal of this series, is to understand curvature. Think about the surface in space, like a mountain, right? Steps. So that sort of thing. So the surface in space is curved intrinsically. It has nothing to do with how you choose a coordinate system. The degree it is curved has nothing to do with how you choose your coordinate system. So eventually we'll get to something called a curvature tensor. So these in themselves are independent of coordinates. And that's exactly what tensors are meant to study. Well, why do we have these transformation law? The transformation law describes how the components of tensor transform under coordinate transformation, because the underlying geometry has not changed when you change a coordinate system. Different components, okay, sorry, say not different components, but components in different coordinate systems should be related in a way. Should be related in a way. And perhaps the best way to appreciate this point of view is to go back to the 25th stream called Tensor Analysis Modern and Classical. Okay, so the simplest example is just to consider a vector space. Consider a vector space. So a vector in a vector space should be a geometric object. It exists on its own. It shouldn't depend on how you choose your bases or coordinate system. Right? So let's imagine you have two bases and you expand your vector, extract the coefficients from two bases. And how should the representation, the coordinate representation relate? Well, that's exactly the contravariant transformation law. That's exactly the contravariant transformation law. And this works for vectors in a vector space. And you can also consider quote-unquote the dual space. So in case you're not familiar with dual space is also a geometric notion. It's a geometric notion. So think about taking a measurement, taking a scalar valued measurement of a vector. Right? So that's a function. That's a function. It's called a linear functional, and they consist of the dual space. Think of the dual space. So well, in calculus, we have lots of scalar field, right? Lots of scalar field. So it's like what's a scalar field? Think of a temperature field. Temperature field. So how each point has a temperature. Once again, this is geometric. It has nothing to do with in itself. It has nothing to do with the choice of coordinate system. Right. So if your say temperature field is linear, like temperature. If your temperature field is linear, it increases linearly in a certain direction, and then that would be a linear or temperature field. Right. And for that kind of object, you also have coordinate representation. And this is something called the dual space. And guess what? The object in the dual space transform according to the covariant transformation law. Yes, dual space in the Helmholtz, exactly. So objects in the dual space called the covector transform according to the covariant transformation law. And you also have, consider for the further examples, the bilinear form. It takes two vectors in V and returns a real. Okay, linear in each argument, and you get what? You get a purely covariant tensor. And as a final example, let's say T takes a vector and a covector. Is V times V star to R. And what you get? You get a mixed tensor transformation law. So tensors, fundamentally speaking, are about study of invariance. And the most important invariance we are trying to get to is curvature. And it turns out to be a tensor with four indices in general. Okay, so the curvature tensor we're trying to get to has four indices in general. Okay, so that's the big motivation for tensors. Okay, because geometry, physics, as well as information geometry cares about curvature a lot. Information geometry in particular has its own flavor and priorities, but this is still extremely important. Okay, so this is why we're dealing with tensors. Is that clear? Okay, and shame not so many people watching it. Well, I mean, it's okay. I mean, we're in deep Riemannian geometry territory, right? You know how the series usually works. Typically, the first ones get the most views. Okay, I don't care. Okay, I could not care less about it. Okay? Typically, the first ones get the most views, and then later on the views gradually decrease, simply because of the nature of the material is getting harder and harder. Like, how can you blame people for that? Right? It's just the way it is. So, initially I said, okay, I'm doing this as the part of the preparation for me to prepare, the information geometry stream happening on August the 8th. Right? So this is just pure tensor calculus, which is useful on its own. Right? You don't, yeah. So I mean, it's totally expected, right? It's totally expected. When you start a series, the first episode always get the first views. I mean, go get the most views. This is completely natural, and I don't think that's a shame, because it's because how we the way we do things on this channel. I mean, I try to minimize digression and just chit chat, because I figured, well, I don't mean other aspects of light isn't important, but there's just so much math to do. I just wanted to get your money worth or your time's worth out of these sessions. Okay, so right now I'm trying to show when G is positive definite, you have cosine absolute value less than or equal to 1. Okay, so because let's just, without loss of generality, mu and consider. So what I'm trying to say is lambda and mu at least one non-zero. If are both zero, then you get a zero vector, right? Then the length would be zero. So we're not considering that. So at least one is zero. At least one is non-zero. Okay. So without loss of generality, assume mu is non-zero. Then you have lambda over mu quantity squared, G alpha beta, A alpha A beta, plus 2 lambda over mu, G alpha beta, A alpha B beta, and lastly you got yeah, no worries. Yeah, no worries at all. Like anytime you can come back, right? Math is timeless. Second year econometric, actually. Yeah, Andre, if you have any, of course, if you have any, say, topic that you're particularly interested in, like just let me know. Okay, so think of this as a function, f of lambda over mu. Second year econometric, I don't know, like, because right now we're a bit stretched out, right? When it comes to topic choices, I prefer to have the topic still related to the main theme of the channel. Like, I think Andre, the mathematical statistics stream is perhaps the most relevant to you and the most suitable to your level right now. The mathematical statistics stream. Because right now, measure theory, it is unavoidable that you need a foundation in, first of all, proof writing, and second, real analysis, which depend on your background, like your institution, might not be like standard courses for econometric students. Okay, but don't worry, we have an upcoming stream, actually tomorrow right now we'll be doing an introduction to proofs from scratch. Introduction to proofs. So the proof we'll be doing right now is not rigorous by that standard. Okay, it's not by, but we'll give the most, so to say, from the ground up. Okay, there's no prerequisites for tomorrow's stream whatsoever. You don't even need to know calculus, linear algebra, or anything for that matter to follow it. It's just, okay, what is proof about? And I think it will help with the measure theory stream. Okay, so let's continue. So that's the function, f of lambda over mu, and it should be positive for all. So it should be positive, that is to say, here f of y should be positive for all y non-zero. It should be positive for all y non-zero, and as a result, the discriminant should be greater or equal to greater than 0. The discriminant should be, it should be greater Yeah, just greater or equal to 0 is enough. Greater or equal to 0 is enough. So the discriminant should be for all y. For all y, therefore the discriminant should be greater or equal to 0. And the delta is now 4 for g alpha beta, g alpha beta, a alpha b beta. And actually, Andre, perhaps good news. Perhaps good news. I just want to say it. Okay. Right now, in the measure theory or in chapter 2, measures, that tends to be the hardest part. Actually, that tends to be a harder part because once you manage to define the measures and stuff, integration is actually easy because we don't define measure for fun, right? It's like in probability, what you typically care about is not probabilities themselves, although they can be important, but rather with expectation, all kinds of expectation, mean variance, that kind of thing. So this is just placing a foundation on that. We're doing now is placing a foundation on that, because once you have shown, okay, the Lebesgue integration exists and whatever, the convergence theorem, the big convergence theorem works, then it suddenly it's a lot clearer. Because right now we're almost working from nothing, right? It's like building the foundation of a house from scratch. So that's going to be difficult. And that's where a lot of beginners give up. So I strongly recommend you considering that fact. Actually, it should be less than or equal to, what am I talking about? It should be less than or equal to 0. Yeah. So strongly considering that fact, and if you can, once again, there's no pressure whatsoever. Just try to get through chapter 2. We're doing things deliberately slow in chapter 2 because from my experience, this is where a lot of beginners give up. Topological data analysis, live stream, modern decision series. Right now I cannot commit because there's a lot of upcoming tasks, but I'll keep that in mind, okay? I'll keep that in mind. I hope I can do one sometime this year. Actually, modern decision series will be included in the mathematical statistics stream. So hopefully we'll get there, okay? Just as a short break, okay? I'm a little bit tired now, but we'll do this until 6. We'll do this until 6, so we still have time. So I'm just saying that in the mathematical statistics live, we will cover modern decision theory. On decision theory. So topological data analysis is definitely interesting. I'm very new to that too. But modern decision theory is not new, okay? So let me just say, let me go to my beloved text on probability and stat. So if you guys know, like if you guys don't know, this is the text I use for mathematical statistics stream, the main one actually, the main one. So if I figured if there's something that's worth adding, I will add that. But this is the main one that we're following. We use this one and Kasselenberger for mathematical statistics, and right now we're still in chapter 6. And I do plan to cover chapter 6, 7, and 8. There's some stuff about decision theory. So decision theory is very much related to the hypothesis testing. So we'll do that. First. This is, of course, this is already included in the plan. That's what I'm trying to say. And for topological data analysis, I don't know about the timeline because right now we have lots of stuff going on. We can perhaps schedule a one-off thing. And I do wish to cover point set topology. In some quite detailed manner. In case you guys don't know, right now I have an introduction to proof, a stream schedule, right? You guys probably know that. I posted the schedule yesterday. So you might wonder, where is that leading towards, right? So that's like, first of all, no background assumed, everything from scratch, okay, how to do proofs. And that will lead to somewhere. Hopefully that will lead to somewhere. So the the idea is to learn the basics of how to do proofs, and then study the first two chapters of Baby Rudin. First two chapters of Baby Rudin gives you a lot of topology needed for practical work. So first two chapters of Baby Rudin covers the real numbers and metric spaces. And after that, we will do the actual, the most general point set topology. To the point set topology in Moncrief. Okay, things like open set, closed set, continuous function, compact set. So Marco, if you're a physicist, and you're interested in why would measure theory be interesting? Why would measure theory be interesting? The truth is, it really depends on your specialization of physics. In fact, actually, you can do a lot of physics, even like probability-related physics, without measure theory. So, measure theory is about the study of sizes. So that's a very general topic, right? So it's about study the size of a set. Probability is just one example for that. So a big set omega, that's your sample space, you have an event A. Study the size in the most general sense. Of course, this is inspired by the regular notion of area and volume in Euclidean spaces, but we wish to do this for very general sets, like even you can have omega being a set of functions. So this is very, it's to describe the use of measure theory is very difficult because so many things requires a notion of a size. So many things requires a notion of a size. So this is very fundamental. And let's say, Marco, if you're interested in statistical physics, statistical mechanics, and ergodic theory, ergodic theory. So ergodicity is a notion from statistical mechanics. If you're getting into advanced statistical mechanics, measure theory will pay off definitely. So it really depends on your specialization. Because let's be honest, like measure theory is a graduate level topic, even for mathematics students. Measure theory is a graduate level topic for mathematics student. That being said, measure theory is not a prerequisite for statistics. Okay, I mentioned it on last live stream on mathematical statistics. The role of measure theory here. This is Axler's book on measure theory. We've been using that. The role of measure theory in statistics is as follows. It provides a general setup, convenient setup, for you to formulate problems. You can formulate problems in terms of probability spaces. And it provides machinery to prove convergence theorem. Because, in statistics, we care about what happens in a large sample size, that sort of thing. It gives us a very powerful framework to prove convergence theorems. So that's cool. But let's say if you're an applied practitioner, you're an applied statistician, okay, you don't plan to prove new theorem, okay? Is this still relevant? It is relevant in the sense of literacy. If you're an applied scientist, if you're an applied statistician, econometrician, chances are you will be reading other people's text, other people's work, the method they developed, and they will be using this language. So even though you don't need to prove new theorem yourself, you still need to follow other people are doing. Right? Imagine this. Some guy developed a new method and he wished to articulate things clearly and prove his method works. For that, he uses measure theory. But for you as an applied worker, you want to see whether his setup for the problem actually applies to your problem, right? So let's say you have a concrete problem to work with, and this guy proved a general result, a general method, but you still need to determine whether or not his method is applicable. So you need to be able to translate the language of measure theory into actual, in terms of actual real world situation. So that's the role here. So measure theory for a statistician, econometrician, works like a lingua franca. So because other people speak in it, you need to speak the same language in order to communicate. Okay, so that's the idea. It's not that you need measure theory to say in a particular practical problem. You can still do a lot of it without measure theory. So the idea is like we've been doing things like, for example, the sufficient statistic. We spend a lot of time on this because it's quite a hard concept and it's quite fundamental. I will say this: the theorems regarding sufficient statistics so far are not rigorously proved. Okay, on our stream, we only prove it for, say, for example, discrete random variables. And measure theory allows you to prove the same result, but for a much more general class. Right? Since I will be going to work a lot with discreteness, maybe it would be useful to actually, if you work with discreteness, then measure theory would probably not be terribly useful. Actually, if you, let's say, if you work with Marco, if you going to work a lot with discrete mathematics, then probably measure theory would not be the best time to spend, best thing to, I mean, the priority for you to spend your time on. Okay, so I don't know what you mean by discreteness. Do you mean things like graph theory, combinatorics, that kind of stuff? Graph theory, graphical model, that kind of stuff. If that's the case, I do not recommend. I do not recommend measure theory as your first priority. Of course, this is important, as I said, as just it's like, okay, in Newton's time, scientists communicate with Latin, right? So that was the common language among scientists. To think of that, measure theory is the common language between probabilist and statistician, right? And it's scientifically, not just linguistically, scientifically provides, as I said, a general setup for you to prove convergence theorem, law of large numbers, that kind of stuff. And let's be frank. Let's say if you're a physicist and try to understand stochastic differential equation. Of course, nowadays you have dedicated volumes written for physicists on stochastic processes and whatnot without measure theory. You have that. However, these are usually translated from mathematical literature to, so to say, to hide some of the measure theoretic details so that people without the background can follow. If you have that background, you can have access to first-hand literature. Okay, so that's what I'm trying to get across. Okay, it's a kind of like in applied mathematics, the lingua franca. In applied mathematics, the lingua franca is functional analysis. Once again, most applied mathematicians, okay, including myself, would not are unlikely to prove new theorems in functional analysis because that's simply not a priority. Okay, but still, you need functional analysis to understand the papers, understand the literature, because the most of the papers write in that language. Okay, if you say you want to study statistics and you don't have measure theory, don't worry. The main intuition and correct application is still available. You can still apply mathematical statistics correctly, precisely, without knowing measure theory. As I was saying, for example, the notion of sufficient statistic can be understood without it. However, the theorems regarding sufficient statistics in our streams only prove for special cases. General treatment requires measure theory. That's just unavoidable. Okay, so there's that. And actually, Marco, if you're interested, go search up on the channel. Actually, let me just put that in the in chat because that's very relevant. I think a while back when I was still doing book reviews, I made a video on how to, called Stochastic Calculus Beginning Level Text for every field, including for physicists. Okay, so there you go. Here, this is a video, so go check it out. I'll copy it down or something. Yeah, I mentioned what I call in the video the elephant in the room. What I said in the elephant in the room, do you need measure theory? And to what extent? I answered that question over there. And I emphasized, let's say, how if you're a physicist trying to understand stochastic calculus, how is it different, say, compared to someone interested in financial mathematics? Okay, so for these two different specializations, the level of measure theoretic detail needs to be known are greatly different. So, and it's difficult, say, for anyway, it doesn't matter. So I was saying that measure theory, we don't on this channel treat this, although we will go over the details. Okay, we won't just skip a proof because we just you just apply the theorem. That's not what we're trying to do. Okay, we are gonna bite the nails and do the details like we do in other streams. This is the purpose of the channel. It is up to you to decide as a practitioner, and say, okay, so if I'm reading this paper, if I struggle with it, is it because I don't know measure theory, or perhaps it's something else? Okay, because it's important to manage your time wisely, especially at a research level, right? Beginning research level. So when you cannot understand a paper, so try to narrow it down. Is it because I don't understand measure theory, or is something else? Okay, and what I'm doing is try to make measure theory as approachable as possible. Okay, I'm revisiting this stuff. Okay, I'll be honest. For example, I know the general flow of the theory, but I still find some of the proofs a little bit unnatural. Okay, so for example, last Thursday, we were trying to prove that the sum of two measurable functions is still measurable. Sounds like a simple statement, no? The sum of two measurable functions is still measurable. However, the proof is very involved, actually. And it involves a special technique, which I could not, where is it? Yeah, is here. The sum of two measurable functions is still measurable. It requires a very special technique, and I couldn't, if I didn't read it, I couldn't recall it. Okay, of course, when you do statistics, you've seen this stuff before. Even though if you can't remember the detail, you still the measurable function forms a vector space. The sum of two measurable functions is a measurable function. It's like the sum of two random variables is still a random variable. It's such a common fact used in statistics, and you can take that fact as so to say well established for the vast majority of the applied work, and don't be worried about if you add two random variables together, is it still a random variable? Typically, you don't need to worry about that. And here's I have the proof for that. Okay. Anyway, so let's close this up. Hopefully that clarifies things a little bit. And now let's come back to vectors and tensor stuff. Coming back to vector and tensor stuff. So right now we're doing this proof of the Cauchy-Schwarz inequality, basically. And this way you get G alpha beta A alpha B beta less than or equal to square G alpha beta A alpha A beta. Okay, so because right now I already have a lot of commitment on the channel, by commitment, I mean a staple stream, staple video series that will go on until, I mean, I wouldn't call it finished because there's really no finish in any regular in any field, right? So I wouldn't call it finished, but most of the basics done. So I don't want to commit to new absolute massive subjects like topological data analysis. Okay? And quite frankly, I'm very close to being burned out. Okay, I mean, let's be honest, but don't worry about me. But I just want to keep things slightly a little bit, slightly concentrated. Every now and then, I can take viewer requested streams. All right, so this is done, and compare this to the classic proof of. Compare this to the what we call to the Cauchy-Schwarz inequality. This is essentially the Cauchy-Schwarz inequality. Cauchy-Schwarz inequality in linear algebra. Okay, so you got the axioms for inner products. So we assume inner product behaves this way. So first of all, you got non-negativity greater or equal to 0 equals happens if and only if x equals 0. Okay, so that's the first one. Second one, you got the symmetry property. X and y inner product equals y and x inner product. And third, you got the property of bilinearity. So a x plus by and z inner product is no worries, Marco. Thank you for joining the stream. And ask fantastic questions. Okay. So yeah, we try to explain motivation of not just concept, but why we spend time on certain subjects. Okay, as clearly as possible. So this way, you get to make the decision whether this is worth your time. So this is axiom of inner product, and now, well, you know, I'm applied mathematician. I'm an applied mathematician. I consider myself a very practical person. So the way I approach math and just things in life is, I want to do things on a need-to-know basis. Okay, I want to do things on need, especially for commitment like learning a math subject and whatnot. You want to make sure this is worth your effort, and not just because, oh, this is beautiful. Like for me, that doesn't seem very informative. Okay. Anyway, so this is the axiom of inner product. So we wanted to show the Cauchy-Schwarz inequality. The Cauchy-Schwarz inequality says x and y inner product absolute value is less than or equal to the square root of x and x inner product and the square root of y and y inner product. So these are all coordinate independent notional vectors. Okay, so inner product behaves this way. So to prove this, so what this really is saying, okay, this really is saying that the projection of a vector x onto the vector y must have length less than or equal to the hypotenuse. Because as we've seen earlier, Cauchy-Schwarz inequality essentially want to show cosine absolute value less than or equal to 1. Right? So this just says that the projection is less than or equal to the is never going to, the projection is always less than or equal to the actual length of the vector. The projection of x onto y cannot have length greater than x. That's what we're trying to show. So given that in mind, perhaps it's not that unnatural to consider an arbitrary vector along the direction of y. Right? Because the projection is a vector along the direction of y. So let's consider an arbitrary vector in the direction of y and consider the distance between x and it. Okay, so this is y, and here let's say this point is ty, and you're considering the length of ty. So from the picture, it should be clear that ty has a minimum length. It should have a minimum length, and it should be non-negative. And the square length of this function, understandably, should be a quadratic function in t. So let's define the function f of t to be the length of the vector x minus ty. Okay, x minus ty square length. Of course, this is greater or equal to 0. Okay, so now let's write f of t as a quadratic function. So f of t is now x minus ty dot with, or not dot, but inner product, x minus ty. Let's say expand that, you get x and x minus 2t x and y, and plus y and y inner product times t squared. Quadratic function is t, so delta, the discriminant should be less than or equal to 0, and therefore for x and y inner product squared minus 4 times the inner product of x and x itself times y and y itself is less than or equal to 0. So this we have CS Cauchy-Schwarz inequality hold. So this is essentially the same proof. It just saves you some writing, as you can see, because of the lack of indices. It's the same proof. It saves you some writing. So that's why a lot of mathematicians prefers index-free notation for that reason. But essentially, we just proved the same thing. Okay. Anyway, and now let's see what else. What's the next concept here? Can we at least get to Christoffel symbol? Let me see. We have an hour. We'll try to do Christoffel symbol. We'll come back to more examples later, okay? We'll come back to more examples later. We're not doing everything from a linear fashion. Because in this section, even though as interesting as it is, there is a mini introduction to special relativity, actually. Yeah, it's a great book. The book, I mean, in the description, Vector and Tensor Analysis by Harry Lass, is a great book. It has so many topics, math and physics stuff. So go check that out yourself. I'm just saying that in this very section, there is a mini introduction to special relativity. So yeah, go check that out. But right now, I really want to get into Christoffel symbol. Yeah, awesome. Thank you very much. So yeah, I want to get into Christoffel symbol. Okay, so to do so, we introduce the notion of geodesic. So geodesic in Riemannian space. Shortest, the curve of shortest length. Geodesic in Riemannian space. And to do that, we'll take a little bit of a detour to calculus of variation. Geodesic in a Riemannian space. So, as I was saying that yesterday, so what does this formula represent? Actually, yeah, it was yesterday. So what does this line element represent? How do you interpret the ds squared? How do you interpret the ds squared in the Euclidean space? Well, when we write ds squared equals dx squared plus dy squared plus dz squared, we actually means arc length formula. So, if you have a ds squared in a Riemannian space, it should also have a similar meaning. This formula also has a similar meaning, and indeed it does. So, if you have a curve, given a curve, say xi of t in Riemannian space, Can we define its arc length? Yes, we can. Its arc length is s equals from t0 to t1. Okay, the square root of g alpha beta, I'm going to use the physicist notation and write the derivative with respect to t as dot. Okay, so this will be x dot alpha and times x dot beta dt. So that's the formula. So we wish to extremize. Okay. So of course, finding maximum and minimum values are not the easiest thing, and sometimes we don't even know if maximum and minimum exist. But let's just ignore those issues for now. Okay. Assume there is a maximum, or just simply call them stationary points. So if you wanted to extremize, okay, such a quantity, how should the curve behave? So we wish to extremize a functional. This is a functional of the curve. Functional of a curve. So we want to minimize that, and we will do some calculus variation. Going back to the basics of calculus variation. So geodesic in a Riemannian space works like this. So recall arc length of curve in a Riemannian space. Right, so we're dealing with s equals the integral from t0 to t1, and then the square root of, as I said, g alpha beta, x dot alpha, x dot beta, dt. Okay. This is arc length. So we need to verify the following claim. Okay, it is said in the text that the goal is to extremize S. So think about this. Let's say this is a Riemannian space. Once again, I'm going to represent it using a torus shape. This is your M, a Riemannian space. Okay, and say starting from 2 points, starting from 1 point, you want to get to the other distance as quickly as possible. Okay, so think of, let's say you live in the middle of a mountain. You live in the middle of a mountain, and you want to get from point A to point B in the shortest distance. And the distance is measured by the what's called g. Yeah, the distance function is described by g. The metric tensor is given by the metric tensor. So you wanted to choose a path that minimizes your distance, right? It would not in general be the best option to simply look at the map and you see, okay, point A and point B, and you draw a straight line from them and call that your shortest path. It might not be working that way. It might not be that way, right? Because the map is flat, but the mountain is curved, so the straight line on the map might not be the actual straight line in the physical space. In the physical space, the distance is given by this formula. So you wish to choose your curve so that S is minimized. So let's say it's very possible that in your actual physical space, the arc with the shortest length may not look like a straight line on the map. So it might be, okay, in the actual space, the curve that minimizes the travel length is like this. Okay, so that's our motivation here. The goal is to extremize S. And here it says by the calculus variation. By the calculus variation, you need to express this. You can express this as what we say. Let's call it, rewrite this as a hang on. Let's call this f. Okay, let's just call this f. So this is t0 to t1 f of x of t dt. The idea is using a slightly different curve that vanishes at the start and no, actually, Marco, we'll revisit not revisit, but just a crash course on calculus variation. So first, I'm just going to write the function as such. Okay, write the function as such. So you can think of this as a function of x dot. You can think of this as the integrand as a function of x dot. Okay, but really, it is a function of f of x dot. It's not a function of a single variable. Okay, it's a function of multiple variables because this is the square root of a quadratic form. It really should be f has n argument. Okay, f has x1 all the way to xn, n-dimensional Riemannian space. Okay, so let's say this curve right here minimizes the distance. So by the calculus of variation, we have the condition for extremal solution, or shall we say stationary solution. Stationary solution, and by the way, this is very useful for classical mechanics, variational formulation of classical mechanics. Stationary solution satisfies the following. Satisfies with d over dt, regular derivative, d over dt, df over dxi dot, minus partial derivative df over dxi equals 0. Okay, so that's the calculus variation. So we need to take a little bit detour from calculus variation. If you have the book by Lass, it says see section 40. See section 40. Let's go to section 40, shall we? Now, this book is a gold mine. It's surprisingly short, actually. It's 360 pages, and there's so much mathematical physics in there. Section 40 has a crash course on calculus of variation. Section 40. All right, so let's go. So if we go to section 40, we have the following problem. So, there you go. So if you go to, I'm just going to say, if you go to page 84, section 40, page 84, section 40. So it says, our problem is to find a function y equals y of x such that the integral from a to b f of x of y and y prime. So here y is treated as a function of a real variable and a real value. Okay, so this is from R to R. from real to real. So y is from real to real. So suppose we're interested in minimizing this functional or extremizing this functional to find y equals y of x such that this general looking integral is extremal. Calculus of variation, by the way, is as old as calculus itself. Newton's Principia investigated a problem in calculus of variation. So Newton discovered the law of fluid drag, and he was trying to discover the shape that minimizes the. You say, okay, ds equals 0 and t0 and t0. Well, s, you see, what you really want, the stationary solution, okay, let me just put it that way. The stationary solution, it should be delta s, the first variation, equals 0. Okay, s, this is a function of x, is a functional of x. So imagine if you perturb your optimal solution a little bit, it takes the input as x, so it should be delta s over delta x equals 0. If you change your function by a little bit, this is what stationarity means. Okay, s is my point is s is not a function of the endpoint, or at least s is not a function of the endpoint only. Typically, in this problem, okay, in the problem of geodesics, the endpoints are fixed and the curve is uncertain. Right? So imagine you live on this weird-looking space. This is your home, A, and this is your school, B. You want to get from your home to your school, B, as quickly as possible. The points are fixed, and now you have to make the decision of what route you choose. Right? Stationarity means, we'll explain that in a second in detail. So stationarity means if you perturb your optimal solution by a little bit, or stationary solution by a little bit, s pretty much stays the same. Right? It's like in regular calculus of a single variable, near the maximum or the minimum, the derivative, first order derivative is 0. It's like the Fermat's condition. Isn't it delta f? No. This notation in physics is called. Sorry, I'm a little bit. I stutter a lot in real life. Okay, I'll try to speak more slowly and steadily, and try not to rush things. This is delta s over delta x. It means the distance s. S is the arc length. It means the arc lengths pretty much don't change if you perturb your stationary solution by a little bit. Here, this is optimal. Here, I imagine this is the shortest path. Okay, this is shortest, and if you perturb it by a little bit, arc lengths pretty much don't change. That's the idea. Not delta f over delta x, delta s over delta x. X, this is a function, not a variable. Okay, not a variable. So x of t is a curve. My bad. I should probably write that of a curve xi. It's good to clarify things. The arc length of a curve xit. xit. So t is an independent variable, and xi are the coordinates in the Riemannian space. Hi. So does that make sense? It's like imagine sailing a ship, and of course, at each point at any instance, the ship can be seen as a point on the surface of the Earth. So the point can be described by two coordinates, longitude and latitude. So over time, both coordinates change. So that's your xit. So let's say if you want to sail from New York to, well, I don't know, maybe London as fast as possible, in the shortest distance possible. This is the functional that represents the distance. And now you wish to minimize that. The stationary condition says if you perturb the optimal solution a little bit, the distance pretty much don't change. Okay, hopefully this is clear. This is extremely important. The fundamental problem setup of calculus variation. Okay, excellent question. So the problem here, as I said, is to find y of x such that the function no is an extremo. Little f is given. Okay. Little f is given, and y of x is unknown. Now think of this as s as a function of y. Y is unknown. So, okay, so what we're going to do is we will show the condition that minimizes the functional. Okay, so there's that. So the extremal solution y of x satisfies the following: d over dx, okay, d over dx, df over dy prime. Df over dy prime, it just means the derivative of f with respect to the third argument. This is what it means, okay? And then minus df over dy equals 0. And this is called the Euler-Lagrange equation. Euler-Lagrange equation. So what does this mean? So this is pretty much the equivalence of the Fermat's condition in regular calculus. We all know the Fermat's condition in regular calculus. So Fermat's condition says at the extremal point the first order derivative is 0. Assuming the extremal exists. Euler-Lagrange equation says to minimize a functional, the optimal solution satisfies this. It's the same idea. Okay, the Fermat's result, Fermat's condition, sometimes called the first order condition, in the context of calculus of variation, is exactly Euler-Lagrange equation. Okay, so let's show that. Do that real quick. And we'll apply this to the study of geodesic. And by the way, in the geodesic, as we mentioned, there's multiple variables. Here we only have a scalar value function, right? You have multiple components in the equation for geodesic, and you just need the Euler-Lagrange equation to hold true for every coordinate, for all I. That's the Euler-Lagrange equation for vector valued function. Is that clear? Once again, this is extremely powerful in mechanics because most mechanical systems has more than 1 degrees of freedom. So there you go. All right. So here let's show the derivation of Euler-Lagrange equation. Once again, we follow page 84 in Lass's text. Okay. So suppose you have, is there any boundary conditions? I suppose there should be any boundary conditions, huh? There should be boundary conditions. Okay, so we're going to assume that given boundary condition, I mean, this is suffice for our purpose. Oh, hi, Leo. Hey, did you change your profile picture? So the boundary condition is y of a equals y of b. Oh, not equals y of b, okay? Y of a and y of b are both given. That's what I'm trying to say. Y of a and y of b are fixed. It's just like in our geodesic problem, okay? You have your coordinates for your house and the coordinates of your school. So these are fixed. You're all phased now, okay? That's great. Um, awesome. Guys, if you guys don't still haven't followed Leo yet, go ahead and do that. He's very knowledgeable and streams and uploads posts on regular basis. So, yeah, and he does mostly pure math and theoretical computer science stuff. Okay, so if that's something that you're interested in, which I strongly recommend you consider that, because one of the main purpose of this channel is to bring different disciplines together. Okay, we do mostly applied math on the channel, but at the end of the day, this is just a social specialization. Okay, there's no scientific distinction between pure and applied math. There's no epsilon delta definition saying, okay, this is applied, this is pure. There's no such thing. It's just different specialization. And Leo, in particular, he taught me some category theory last week, which I really enjoyed. So go ahead and follow him. The derivation for Euler-Lagrange equation is as follows. So let's first draw the picture, all right? So you have this curve. Imagine you have the extremal curve, y of x. This is y of x. Extremal solution. Oh yeah, I have a big video coming out tomorrow, probably putting more things, everything else in my channel combined. That's cool. Awesome. Thank you so much. History and future computation. Well, is it about numerical analysis or just like a CS stuff? Okay, so this is extremal solution. And let's write that. Bro, you use this tilde thing in your like in your chat. That's so Asian of you, man. Anyway, I'm not trying to stereotype. Okay, it's just that it feels to me a lot of Asians type with this tilde sign. It's a cultural thing. I'm a tilde guy. Okay, that's cool. Yeah, it really is, right? It's an Asian thing. You know that, man. Like you're more Asian than me. I tend to like add a smiley face at the end. That's so funny, man. Goes from World War II all the way to reasoning machines. Wow, that's so cool. Awesome. Right, so it's more theoretical computer science, right? It's not numerical analysis. I was thinking of computation because I tend to associate computation with computational mathematics, aka numerical analysis. Okay. But it's cool, theoretical computer science. I should definitely learn more about it. Okay. Anyway, so I was saying, let y equals y of x be that function that extremizes the function. The functional s of y of x, s of y. So I guess, is it fair to say that you and JC are more algebra type of person? Okay, cool. It's one more orphans numerical analysis, simulation regression though. It's okay. That's totally fine because nowadays numerical mathematics is more similar to. So I would say in terms of the content, the modern numerical analysis is closer to functional analysis, that is to say, a branch of analysis than to computer science. So it's totally okay to leave that out. It's so different from theoretical computer science now. Yeah. Yeah, I'm like algebra and cryptography, lots of little stuff. That's cool. Yeah, that's cool. So, um, yeah, on JC's channel, I was referred to as an analysis kind of guy. I guess it's fair because, I mean, even though I don't consider myself as a dedicated analyst. Applied mathematics traditionally uses more analysis, say algebra, right? You need like things like differential equation, which naturally connects to real analysis, complex analysis, functional analysis, right? And probability and stats, measure theory, that kind of thing. So if I talk about pure math, it's highly likely to be that kind of stuff. But yeah, not because I'm a dedicated analyst. Anyway, so let y equals y of x be that function that extremizes the functional. And let's consider the perturbed version. So on the picture, it looks like this. So you imagine you perturb the optimal solution by a little bit. And let's give that a name. Let's call that big Y. Call that big Y bar. Why not? I like the characterization of algebra as the domain of equation and the analysis of domain of inequality. Did I say that? Did I say? I feel like I've said that somewhere. I'm pretty sure I'm not the first one who said it, but I did mention that somewhere. Like I think I mentioned that in my video called "Is dx squared really zero?" Right? Because in applied field, you often, let's say, ignore higher order terms, something like that. Physicists know all about it. Ignore dx squared. Right? So I see. Okay, cool. Fair enough. I think I mentioned that in my video on dx squared equals zero. So hang on, Let me just. I gotta feed my cat real quick. Okay. I'll be feeding. I'll just feed my cat real quick. All right. Be back in a minute or two. Yeah, I'm back. So okay, cool. Cliff Taubes. I think I might need to check that out because right now we're doing the differential geometry related stuff. Okay, so what I was saying that you have the perturbed solution, perturbed function, y bar. So let y bar of x with the parameter alpha defined as the optimal solution y of x plus alpha times phi of x. Okay, so phi is arbitrary. Assuming differentiability, all those good stuff. Okay, so phi is arbitrary. Okay, assuming the C1 is continuous, it has continuous first derivatives. And phi A equals phi B equals 0. So this way the boundaries are fixed. Okay, with phi is arbitrary, C1, phi equals phi B equals 0. All right, so, and also alpha is arbitrary. This is how we describe a perturbation. Okay, so because of the stationarity, we should have, let's call this J, okay? Denote J of alpha, denote J of alpha as the integral from a to b f of x big Y bar prime dx should satisfy is extremo. When alpha is 0. And this is extremo when alpha is 0, because when alpha is 0, big Y bar is just little y, and little y by assumption is the extremo curve. So as a result, and thus J prime of alpha is 0, because alpha is just a number, arbitrary real number, okay? So J prime of alpha should be 0. That's the Fermat's condition. And it turns out that this reduces to the Euler-Lagrange equation. Okay, so let's do that. So let's calculate that, all right? So here, what is dj over d alpha? What is dj over d alpha? Let's try to figure that out. So assuming you can differentiate under the integral sign, and alpha equals 0, okay? So let's do that. There will be d over d alpha of the integral from a to b, f of x, y bar would be y plus alpha times 5, okay? And the derivative of y prime is, of course, big Y prime is, of course, little y prime plus alpha phi prime. Okay, so that's the integrand, the new integrand, which depends on alpha. And now we assume you can differentiate under the integral sign. Okay, assume you can differentiate under the integral sign, so that brings us to integral from a to b. Okay, the first term has nothing to do with alpha, so it just becomes df over dy, which means y takes the derivative with respect to the second argument. Never understood differential geometry well. Maybe I should read that book too. Okay, great. I'll check that out. I mean, my understanding of differential geometry, once again, is rather incomplete, because, you know, I learned geometry from a computational perspective, quote unquote, like tensor calculus way. I'm trying to do that, like revisiting that now, but it's been so long. It's over 10 years, actually. I said 10 years, but it's actually over 10 years. I think I first learned it in 2015. Yeah, it's over 10 years, and I didn't have much opportunity to practice it, so it kind of atrophied. And then I learned, and years later, I learned separately point set topology, but I never brought the two together into understanding of how, like, modern differential geometers see the actual subject, right? So yeah, it will be a great opportunity for me to first of all get rid of all the rust, okay, and then get some new insights. Okay, so this is we're taking this the derivative with respect to alpha. Okay, we're taking, so to say, I mean, do it more slowly. So this is differentiating under the integral sign, df over d alpha. Terry has some notes like basic differential geometry. Okay, cool. Ah, I see. Is it on his blog or his actual book? Tao's differential geometry notes. Is that a book or is on his blog? Okay, so differentiation under the integral sign. That's the operation. And now we just use the chain rule from regular calculus. Oh, by the way, you need to set alpha equals 0, okay? At the end. A block, okay, great. Yeah, his block is really amazing. Anyway, so here, perhaps this is not a good notation, but rather let's write it this way: d over d alpha as a whole, okay? Not a partial derivative of f with respect to alpha, because that wouldn't be accurate. But instead, the first argument x has nothing to do with alpha, so it just vanishes. So, but instead you have df over dy, meaning the partial derivative is taken with respect to the second argument of f. Okay, and then times phi, and then times phi, because you still need to differentiate with respect to y plus alpha phi. So that's just phi. And then plus what? And then plus df over dy prime times phi prime. That's just the chain rule. Okay, so dx. And we already set alpha equals 0, because the way we set alpha equals 0 is as follows. So purely by differentiation, df over dy is evaluated at y plus alpha phi. And by setting alpha equals 0, here the partial derivative means df dy is evaluated at the point x, y, y prime. Okay? You know what I'm saying? So if you're just purely differentiation, the argument is still above, but by setting alpha equals 0, it suddenly becomes x, y, y prime. Okay? So that's the full notation, although it's a little bit tedious to write. So for that reason, we're going to shorten this to be simply df over dx. And it's understood that the partial derivatives of f are all evaluated at the optimal curve, stationary curve. Okay, this is just a convenient notation, df over dy times phi plus df over dy prime times phi prime dx. Okay, so what else? Okay, so we need to integrate this. We still need to integrate this. How do we integrate that? The first term we can't do much about. So let's just isolate that. Integral from a to b df over dy times phi. But the second term begs for integration by part. You know, the second term, because of the y prime thing, it begs for integration by part. df over dy prime phi prime dx. So let's do the integration by part. That's actually the key in the derivation of the Euler-Lagrange equation. And also, if we, and I think I will, if we go back to the stochastic series, we're going to do a stochastic series live, or stochastic calculus series live, or as a video, we'll derive the so-called Kolmogorov forward and backward equation. And the key is still there. It's still an integration by part. And I don't think it's very hard to think about this. If you've done enough calculus, you see y prime and dx, immediately you think about integration by part. By parts. Okay? So this way, you get integral from a to b df over, oh, I missed the dx, df over dy phi dx, and then plus what? This is d phi, right? So you should get a product that's df over dy prime times phi, upper and lower limits are b and a, and then minus the integral from a to b times what? Times d of this partial derivative. So this way you just get phi times d over dx, partial derivative df over dy prime times dx. And because of the boundary condition of phi, you see, because of the boundary condition of phi a equals phi b equals 0, the first term, this vanishes because of the boundary condition, equals 0, due to boundary condition. And now you can bring the integrals into a single integral, and notice that phi is a common factor. So it's an integral from a to b, phi times df over dy minus d over dx, df over dy prime. So you pretty much have the Euler-Lagrange equation. Okay, you pretty much have the Euler-Lagrange equation because, well, to finally get that, you need a continuity argument. So assume this is continuous, the integrand is continuous, and phi is arbitrary, so it has to be 0 everywhere. The integrand is continuous, phi is arbitrary, and C1, so this has to vanish. There is something in, I think it's called, what's called? Some French name. There's a lemma that actually justifies this. Let me just quote that. So we're still not completely abandoning rigor in this stream. It's called Dubois-Reymond. Dubois-Reymond lemma, also known as the fundamental lemma of calculus of variation. There you go, here. Fundamental lemma of the calculus of variation. So it says, if a continuous function f on an open interval ab satisfies the equality for all compact supported smooth function h. So h is, we call a compact support smooth function, which means it's non-zero only on a compact set, like closed and bounded set. This is what we call a test function, typically, in calculus variation and functional analysis, distribution theory, and all those things. So if we have that, then f must be identically 0. So it really is a continuity argument. So this is called the fundamental lemma of the calculus variation, and it's also useful for deriving PDEs. Okay, and here, yeah. So okay, yeah. As you can see, the lemma is used to prove the extrema of the functional satisfy the Euler-Lagrange equation. Plays a prominent role in classical mechanics and differential geometry. So yeah. So and this by the fundamental theorem of the calculus of variation. Calculus of variation. So this way you get the Euler-Lagrange equation, d over dx of partial derivative df over dy prime minus, typically you write it this way, okay, df partial derivative df over dy equals 0. There's that. Okay, so we have this Euler-Lagrange equation, and now let's think about our problem. So we wanted to minimize the arc length, don't we? We want to minimize the arc length, and now we have the Euler-Lagrange equation should tells us what differential equation the geodesic satisfies. Okay, so can we simplify this stationarity condition? Is Euler-Lagrange equations, because there are multiple coordinates in general. All right, let's see. Well, so coming back to the geodesics this is a crash course on calculus of variation, so I'm going to just put it with a separation line here. All right. How do we apply this? Right. How do we apply this? So we know, let me just copy this and continue down in the note, df over dxi dot minus df over dxi is 0. And f is what? F is the square root of g alpha beta metric tensor times x dot alpha x dot beta. This is f. And remember, f in general is a function of, let's just write it that way, f should depend on, in general, okay, in general depend on t, xi, t, xi, and xi dot. Okay, so now let's substitute this expression of f into the Euler-Lagrange equation. And that should give us the differential equation satisfied by the geodesic. Okay, here we go. So geodesics is given by the Euler-Lagrange equation, and see what kind of simplification we can do. Okay, so well, as you can see, it only depends on, hang on, does it even depend on x? Oh yeah, it depends on x. Remember, I was initially thinking, oh, it only depends on x dot, that would be cool. So this term vanishes, but no, actually I was being naive. Remember, g, the metric tensor, can vary from point to point. Right? This is even the case for some coordinate system in Euclidean space. Only if you use the Cartesian coordinates, here, where is that? Here. Yeah, only if you use the Cartesian coordinates in Euclidean space where you have g is a Kronecker delta. Well, that's a special case. I mean, in the Euclidean space, g can be a constant everywhere. But it doesn't have to. Even in Euclidean space, you can have curvilinear coordinates, such as spherical coordinates, where g is non-constant. It depends on the location, or depends on the coordinate. So in general, g, okay, the metric tensor is a function of the coordinate. So that's why here, you cannot treat g alpha beta as a constant, but rather g alpha beta is a function of x1 all the way to xn. Very important to be mindful of that. G is not a constant. In general, it's not. So, what do we have? Well, the square root business is a little bit troublesome, but it's okay. df over dxi, you get 1 over 2, and then g alpha beta x dot alpha x dot beta to the minus 1/2, and then times d over g alpha beta downstairs over dxi. Okay, so really it's just 1 over 2f. Okay, 1 over 2f times, oh, I forgot, you still need to multiply by x dot alpha x dot beta. Okay, still need to, because these are treated as independent variables. Okay, in the function f, xi and xi dot are treated as independent variables. The function value doesn't know its derivative. Okay, dg alpha beta over dxi, x dot alpha x dot beta.
So yeah, that's the df over dy term here. And now we need the other derivative, which is harder. So first, let's first not do the time derivative. Just say what's df over dxi dot. What would that be? Okay, so well, remember how we differentiate quadratic form? Remember how we differentiate quadratic form? Perhaps this is not the easiest thing to remember, but we did that earlier. Tensor analysis 23rd. We did that on 23rd right here. I think we did. How to differentiate a quadratic form. Yeah, it's here. So here, S is a quadratic form. I'm just going to summarize that. Okay, this is example 4. S equals A alpha beta. We'll close the stream in 15 minutes. If we can't finish the derivation, we'll continue the tomorrow. Because at 7, I have a measure theory thing coming up. Okay. So S is this, and ds over dxi is A alpha I x alpha plus AI beta x beta. So this is how you differentiate a quadratic form in general. Here we're not assuming A alpha beta is symmetric. So this is quite general. Okay. For metric tensor, we'll use the symmetry. Okay, so let's just get this result to on the side. Change the color to green. Okay. What is df over dxi dot? Well, by the chain rule, you first need to have like a 1 over 2f thing. You get a 1 over 2f thing. And then you need to differentiate d over dxi dot of the quadratic form. You see? We work with square distance as much as possible. In geometry and statistics, nobody likes to work with square root. But here, you have to use a square root because the arc length needs a square root. We're not minimizing the integral of arc length squared. We're integrating over little arc lengths. So anyway, here we need to differentiate g alpha beta xi dot alpha x dot alpha and x dot beta. So that's what we needed. Okay, so 1 over 2f times what? 1 over 2f times, this is, how do you apply this result? Well, you get g alpha I, right? G alpha I, and then x dot alpha plus g I beta x dot beta, using this result on the side. Okay. Okay, so now you have that, and then you take the time derivative, d over dt, or differentiating with respect to the parameter of the curve, d over dt of partial derivative df over dxi dot. Okay, what do you get? Well, you need the quotient rule, don't you? You need the quotient rule, don't you? So, because, or just use the product rule. So maybe, hang on a second. So what do? We do, what is f, by the way? F is, hang on. F can be seen as your f is ds over dt. D little s over dt. D, not big S, okay? Let me emphasize that. This is big S. Big S is a functional of the curve. And here, little s is just the speed of the curve. It's just the speed of curve, little s. Speed. Okay, and here, can we write this as follows? Let's say use the product rule. I mean, just regular calculus stuff, I guess. You get 1 over 2f times d over dt of this thing. Yeah, so just the product rule. And then plus, well, the time derivative of 1 over 2f, this might be nasty, but it's 1 over 2f squared, and then df over dt. And then df over dt times, well, this thing. Oops, sorry. Yeah, times this thing. No derivative. So try to simplify that. Wait, Marco, what's the question? I'm waiting. Okay, anyway, here we only have 10 minutes. dfx over dfx, oh, df over dx. No, there's no df over dx, huh? Oh, sorry, you mean upstairs partial? What happened to inside terms? Hang on. Perhaps Marco. I'm just gonna point my mouse at whichever place where you have problem with. Okay. Do you have problem with this term? Where, yeah, this right here. Do you have a problem with this? Partial df over dx dot. You mean this? What happened to inside term here? This is this part uses this example here because you see this is a quadratic form. This is from example 4 on the 23rd. Here we derive this formula. This is a quadratic form, and the first derivative, or the gradient, you can think of this as a gradient. ds over dxi is this thing. And we're just applying this, okay? Okay, cool. I'm glad we got that cleared up. Okay. So, here, let's see. What we have here is 1 over 2f, 1 over 2f, and inside you got g, let me see, g, at d, the derivative now looks like g as a g alpha I x double dot alpha. Okay, plus
plus d over dg alpha I over dg alpha I over, because you see g alpha I in general depend on many things. So let me just do things a bit slowly, okay? So we're in the most difficult part. No worries, no worries. I'm happy to do this. D over dt of g alpha I, and there's already a small community of math streamers going on YouTube. Go check out Leo from Leo Lectures and JC Practices Math. And I'm glad that we all kind of have our own specialties. This is mostly, my channel is mostly applied mathematics, and Leo does pure math and theoretical computer science. And he's posting a video tomorrow, so very excited. D over dt g alpha I times x dot alpha, right? Just the product rule again. And then you got gi beta x double dot beta, and then plus d over dt gi beta. Yeah, you're great. Okay. So we don't have enough casual stuff going on the channel because I just have so many different things to do. I wish I can have like a more casual, perhaps after this, because I have a lot of plans. Maybe we can chat with you guys a little bit. So I just want to finish this derivation and close the stream. Let's see if I can do that. Okay. All right. So what about this thing? Okay. What about this thing? And of course this thing as well. How can we simplify them? Remember, G alpha I, right? G alpha I are functions of xi. So I'm going to use another perhaps familiar identity on first day. I said, if you, let's say, have a function f of variables x1 all the way to xn, then the derivative df over dt is as follows. So this means each coordinate is a function of t, and you have this chain rule. So we're going to use that. I mean, we didn't write Euler-Lagrange in tensor form. What we're saying is we're applying the Euler-Lagrange equation to an expression with index notation, if you can call it that way. Okay, so Marco, I don't want to oversell things. Okay, we're using the Euler-Lagrange equation to a function whose really is a square root of a quadratic form, but is just written in a tensor notation or index notation. So I don't want to oversell things. So that we're in the heat of deriving Euler-Lagrange equation. No, not deriving Euler-Lagrange equation. We're in the heat of applying Euler-Lagrange equation for the geodesic equation. So this is the last ingredient we use. Basically, it's also a chain rule. Right? Remember, there's a summation implied here. There's a summation implied here. Let me just change the color to. This is perhaps example 1 from day 1. Okay. So we're going to use that and express these two derivatives. Example 1. This is from example 1. So if we continue writing this, it will be 1 over 2f over
let's say this is g alpha I x double dot alpha plus, remember there should be a summation going on, so I don't want to use the alpha index again, so let's just write dg partial derivative alpha I over dx beta times x beta dot times x beta dot is using this identity here, dx beta dot, and then times x x dot alpha. I think at some point the symmetry will play a part, but we will see. Still haven't used the symmetry of the metric tensor yet. G I beta x double dot beta, and then plus here you got dg I beta over dx, let's use the index alpha, and then x dot alpha x dot beta. It's a really complicated calculation, but simply because of the nastiness of the square root, right? I mean, we can't get rid of the square root here. It's just unfortunate, but this is what we get because of it. All right? And the next term we do nothing about. Okay, so, and how can we proceed further? How can we proceed further? Well, remember t earlier was considered an arbitrary parameter here. T is just a parameter that parameterizes the curve. So if we choose a special parameter, we're able to simplify things a little bit. Okay, we're going to choose the parameter t so that ds dt is 1. So that ds dt is 1. This is called the arc length parameterization. So we're going to choose the parameter t so that ds over dt is 0. Does that make sense? It's like you're choosing the parameter t so that the tangent vector is always a unit vector. It is a monster, I know. The geodesic equation is one of the hardest things we have encountered so far. But basically, we're going to make a special choice. We're going to choose what we call unit length parameterization or unit speed parameterization. Okay, so now specialize to unit speed parameterization. That is to say, x dot I has this property that the square length, let's just put it this way, the square length is 1. This is the unit speed parameterization. So that means ds over dt is 0. ds over dt is 1. ds over dt, or df over dt is 1. Sorry, not df over dt is 1, but f is constant 1. So f is constant 1. You can always do that because any vector can be normalized. A tangent vector can always be normalized. Here, t is an arbitrary parameter. You can always normalize your vector to make your tangent vector. X dot is a tangent vector. xi is a curve, x dot is a tangent vector. We choose to parameterize the curve in a way that the unit vector is the tangent vector. You can always do that. Okay, always possible. So this way, the hang on, f, which is ds over dt, is 1. ds over dt is 1 because f is you can think of the speed. This is the speed. This is the speed. So that's the norm of the tangent vector is the speed. So we're using the tangent. This is the length of the tangent vector. So that's unit. and then df over dt is 0. So it kills the second term. And really, this is the most natural choice if you think about it. Why? Because the length is a geometric quantity. It's not an arbitrary parameter, right? The length is a geometric quantity, and if you, if you've seen some, say, theory in what we call the in curves and surfaces in 3D, which, by the way, the book also have. Okay, so if you go to chapter 3, there's a, once again, rapid fire treatment on the differential geometry of curves and surfaces in 3D. Okay, of course, what we're doing is just a generalization of those. So if you still find things lacking motivation, why we choose a unit speed parameterization, and you have question whether this is always doable, go check out those sections. But this is always doable. Okay, so df over dt is 0, right? Because f is a constant. So this way the second term gets killed. So we have that, and also there's this fact that G is symmetric. G is symmetric, so those two terms can be combined. These two terms can be combined. All right, so far what we have here. So just assemble everything. Also, Gij equals Gji. Remember, in this term, alpha is a dummy variable. And here, beta is also a dummy variable. These two terms should be the same due to symmetry. G alpha I x double dot alpha equals G I beta x double dot beta. So you have that. And now we have the following. Euler-Lagrange equation is finally now ready to be simplified. So here you got 1 over 2f of 2, say, G alpha, G I alpha x double dot alpha. Here, yeah, this one. And then plus these two terms. These two terms, actually x double dot alpha, yeah, this needs to be, this needs to say, because even though we know the speed is constant 1, its acceleration might still not be determined, right? So x double dot alpha stays. This term goes away to 1, this term is away, is a 1, this term is a 1, this term is a 1. So you just get the two partial derivatives of g. This term remains, okay? Not the x dot. X dot is just 1. Actually, that's not true, because this is a summation. The components might not be 1. Hang on a second. Yeah. Okay, I need to keep that. Okay, I need to keep that. So keep this as a whole. The component might not be 1. So this, you cannot just say, okay, this is just a partial derivative. That's not right. Okay. Anyway, so these two terms remains. Okay, nice. Okay, so yeah, just to be clear, this is the new d over dt, df over dxi dot, dxi. Is it dxi? Yeah, dxi dot, I believe. Right here, dxi dot. So that's the first term, and then minus df over dxi. So this thing. So we
minus this thing. Minus this thing, okay, equals 0. And also f equals 1, actually. F equals 1, so 1 over 2f goes away, actually. Makes things easier. 1 over 2f actually goes away. Minus this equals 0. Okay, and this is df over dxi. All right, so finally we are now ready to combine the terms. So divide by 2, and notice that the last three terms has a common factor, x dot alpha, x dot beta. So therefore, in its full glory, you got the geodesic SDE. No, not SD, ODE, ODE, not SDE. Thank goodness this is not stochastic. Okay, Gi alpha double dot alpha plus half dg alpha I over dx beta plus dgi beta over dx alpha and minus the last term, which is, hang on, dg alpha beta over dxi. How are these three terms differ, though? Let's see. So here you have this quantity. I'm just going to check the details here, because the indices are very easy to be messed up. Yeah, it does look like there are 3 free indices, you see? There's no summation going on in this term alone. It is when you multiply that by x dot alpha and x dot beta, the indices alpha and beta were contracted. So you see, even though the alpha and beta appears upstairs, they're still downstairs for G. So this is considered lower indices. So this is considered lower indices, all right? So in fact, in this bracket, alpha, beta, and I are all free indices and are all lower indices. Okay, so this equals 0, and now we can use the metric tensor, multiply by g tau I. Multiply by g tau I. So g tau I times gi alpha. This way we get a Kronecker delta. Delta tau alpha x alpha plus g tau I times this thing equals 0. Okay, that's nice. And see what we can do here. Well, the first one obviously is just a index swap. So you just get x double dot tau. X double dot tau and plus, well, there's not much you can do here. Let's just call that, hang on. Let's call that gamma tau alpha beta, because now I is contracted. And then you have x dot alpha, x dot beta equals 0, where gamma tau alpha beta is half g tau I. The book uses sigma. It doesn't matter. I is a dummy index. G tau sigma times d over d of g alpha sigma over dx beta plus dg I, here I is sigma beta over dx alpha, and dg alpha beta over dx x sigma. Okay, so that's it. Okay, so this will be, yeah, this is defined as the Christoffel symbol. Right, this is called the Christoffel symbol of the second kind. So it comes from the geodesic ODE. It is not a tensor, okay? Spoiler alert, this is not a tensor. This is not a rank 3 tensor, even though it has an upper index and 2 lower indices. So, because right now, everything we've seen so far are tensors. Everything we've seen so far with indices are called tensors. This is not a tensor. This is actually not a tensor because it does not follow the rule of tensor transformation. Okay, which, I mean, we don't have time to show it today, but this is called a Christoffel symbol for that particular reason, not Christoffel tensor, okay, called the Christoffel symbol of the second kind. Yeah, I know. I mean, this is completely natural. There's always going to be a point in a subject where things are getting very tough. Right. So, I mean, actually, let me just rewrite this and briefly summarize. What did we do? Okay, what is the overall logic in this monster derivation? Okay, so there you go. We have the geodesic ODE. Let me write that down. Okay, as dx over ds, dx alpha over ds. Yeah, today is not an easy day. But this is simply because we're deep in the territory of Riemannian geometry. And, well, I guess it's perhaps also because of how I did not do the first problem very well. Yeah, it's okay. It's okay. We're going to be closing the stream. It's okay. I will just give a brief summary at the end regardless. So Marco, if you want, you can take a look at the summary. So the overall idea is actually quite straightforward. So you have a curved space and you want to find the shortest path between two given points. So we start from the arc length formula. And the crucial ingredient in the arc length formula is the metric tensor G alpha beta. Right? The integrand is the speed, which we call f. So the integral is integral of the speed. To find the extremal path, we used calculus of variation. This is very natural because S is a functional. S is a function of the parameterization, or actually S is a function of the curve. S is a function of the curve. So the curve is a vector valued function, and to get the, as I mentioned, to get the extremal curve, you need to write down the Euler-Lagrange equation. Okay? Assuming the extremum exists, of course. So this is a necessary condition for the extremal, not a sufficient condition. Okay, so here we have a quick derivation of a general problem in calculus of variation. So you want to minimize an integral or maximize an integral, and the integral function has this given kernel f. Now, f is given. And the key of deriving the Euler-Lagrange equation is to
consider a small perturbation of the optimal solution. This y bar here, small perturbation. And the y bar is parameterized by a scalar alpha. So now the functional you wish to minimize can be treated as a scalar function in alpha, and then you just apply the first order condition in regular calculus. After setting the derivative to 0, we use a crucial step, which is integration by part. And finally, using the fundamental theorem of calculus, which is really a continuity argument, we show that the integrand must vanish. The integrand must vanish, and that reduces to the Euler-Lagrange equation. So that's a separate problem. It's a separate problem that works in all fields of mathematics, and not just here. Okay, so the geodesic problem is really a special problem in calculus of variation. So now it's just a matter of applying the Euler-Lagrange equation to the geodesic functional, right? The distance functional. And to derive that is a little bit of a mess because of the square root. The square root cannot be rid of in this case, because otherwise you just get the integral of a squared speed, which is physically meaningless. So a lot of the nastiness in the derivation comes from this square root. But if we just grind through it and just keep track of the indices, there's not really much to it, okay? There we use some special formulas we derive in the first lesson, the first stream on tensor calculus, including how to take derivative for a quadratic form and also the chain rule. So applying those things, and you get the relevant terms because you got two big terms in the Euler-Lagrange equation. So you can differentiate. Okay, just be very careful and use the formulas we had earlier. Not much going on. And here we have a key simplification that is, because of the parameter t can be chosen to our advantage, we chose the t to be the so-called natural parameter, also known as the unit speed parameterization. That is to say, you let the tangent vector to always have unit speed. And if that's the case, in particular, the first term in the Euler-Lagrange equation, which is the more complicated, can be simplified drastically. One term drops out, basically. That's what happened. And then you combine the terms, and you get this differential equation here. This differential equation for the x dot, for the axis there. And then, so after that, we use the reciprocal metric tensor to get, so to say, to get a x double dot on its own. Okay, and the result is as follows. You get this big complicated numbers of arrays of numbers with three indices, with three free indices, okay? And then times the nonlinear term. So this is a nonlinear term. In general, geodesic equations aren't linear because of the multiplication of derivative. And this monster of a constant, not a constant, monster of a symbol is called Christoffel symbol. And as we can see, it has nothing to do with the curve, but only the metric tensor itself. If you have the G, you can calculate the metric tensor. If you have the metric tensor G, you can calculate the Christoffel symbol. Okay, and perhaps it is instructive to calculate the Christoffel symbol for some special metric tensor, because we already have the spherical coordinate metric tensor in Euclidean space. Okay, in Euclidean, which is a very special example. I think next time we will see how the spherical coordinate. Okay, what's the Christoffel symbol for the spherical coordinate? Okay, and the Christoffel symbol will play a role in information geometry as well. Okay, so that's it for today's stream, and I gotta go now. I gotta drink some water, rest a bit. I initially planned to start the measure series stream at 7. Looks like I have to start at 7:30. Otherwise, I'm dying. Okay, guys, thank you very much for joining the stream.